Sorry?
Is there power up here?
Yeah. What do you mean?
For my computer, because the battery's
There's a power right here.
for a Mac?
Well, what do you want? You want the cord?
Oh,
You're
yeah.
asking
No,
for
I've got the
power.
cord, but I'm just wondering if it's
There's
over
a
here.
power right there, yeah. All set to go? All set to go? Okay, whenever you're ready. Okay. Thank you all for coming to the 30th annual CUNY Sentence Processing Conference. All the information about the conference is on the website, which is the link up there. And we have a Twitter. I guess our Twitter feed is at Language MIT. And if you have any questions or you want to need any information, just use that hashtag or just talk to one of us individually. We're around. This is the 30th CUNY. It's a kind of a round number. I guess we could have another celebration, but we just had a celebration at 25, so I think we're going to have to wait until 40 or 50 for another real celebration. I'm going to tell you about descriptive statistics about the conference everyone submitted. I want to thank, first of all, the reviewers. We had 201 reviewers, which is an enormous number of reviewers. Thank you very much for everyone who contributed to this job. Each reviewer reviewed between 6 and 10 abstracts. We had, I don't know if this is a record, it seems like a lot, 449 abstracts submitted, of which we were able to accept only 45 for talks, which is obviously a 10% acceptance rate, and 264 posters. So an overall acceptance rate of 69% for posters and talks. And there was just a very high quality of submissions, and unfortunately for the ones who got rejected, many of those were actually very good as well. And then of course there's a lot of luck in this kind of a process in getting accepted or rejected. I hope that the people that didn't get in were able to benefit from the helpful comments that many of the reviewers provided. Just for your interest, the scoring, how we did this, everything was reviewed by at least 3, but almost all were reviewed by 4 to 6, 4 and 5. And we just simply removed reviews for which reviewer checked of conflict of interest. And only one of our reviewers got confused about what yes and no were there. Vic. So anyway, but we didn't notice that until afterwards. And then we threw out the lowest score and averaged the remaining ones. And this is our system for selecting the talks, basically, and the posters. It's admittedly imperfect because there's so much noise in these in so few reviews for so many good choices. But this is a simple strategy that we chose. Because we have so many good abstracts, we have shifted the format somewhat. We're following a pilot version from last year at Florida where they had these 15-minute talks. You're probably well noticing that there's, how do we get 45 talks plus 9 invited speakers into 3 days? Well, that's because 33 of those talks are 15-minute presentations, okay? And so, which means, and I'm sure many of you here are 15-minute presenters, that's a 12-minute talk and 3 minutes for questions, which means if you want to ask questions, which of course, the CUNY community wants to ask questions, please be brief. When you're asking a question, come to the mic, state your name, where you're from, and have a brief question. Do not give another talk, especially in the short question period, okay? So because we only have time for 3 minutes. And so the questioners, they have to be, asking a question have to be brief. Of course, I'm assuming the people giving the talks will be on time at 12 minutes. The session chairs are going to have to be ruthless for moving on. So we're going to have to cut discussion. This is a trade-off between having more presentations, having 45 presentations, and having more discussion during the conference. And of course, this question about whether we want to have a single session where everyone comes or multiple sessions. And we favor the single session, which has always been at CUNY, so that everyone sees everyone's presentation. That way we have a better chance of cross-fertilization of people in different fields. Otherwise, we're going to be separated into some more narrow fields than we already are. Anyway, these are all choices, and someone else can make different choices later. We have a special session this year, as I'm sure you're aware, which is sponsored by the Program in Linguistics at the National Science Foundation, which is language processing and language evolution. And from the statement on our website, I'm just going to read along with you that, why are human languages the way they are? The special session at CUNY 2017 at MIT will explore the hypothesis that how language evolves is deeply intertwined with how humans use language to comprehend and communicate meaning. Typically, languages are viewed as arbitrary static objects that humans must learn and use. In this session, we will explore the idea of language as a dynamically evolving product of human interaction shaped by information processing constraints and by social contexts in which it is used. Following this reasoning, general properties of human information processing may explain variation in languages, including differences among languages and differences between grammatical constructions within languages, emergence of languages, for example, home sign, and their development over time. This approach can in turn allow for a deeper understanding of basic language processing mechanisms because it richly characterizes the linguistic systems being learned and used. And you thought you were done? No, there's one more paragraph. The time is now ripe to ask fundamental questions at the intersection of language processing and language evolution. The field of psycholinguistics has arrived at fairly robust generalizations about sources of processing difficulty for humans, including memory constraints and the effects of prior linguistic experience. In linguistic typology, the availability of large public data sets such as the World Atlas of Linguistic Structures has enabled faster, reproducible testing of hypotheses, as well as synergistic communication with other fields. In addition, phylogenetic and statistical methods have provided valuable means of validating generalizations beyond particular language families and geographic areas. In computational linguistics, new large annotated data sets have recently become available which can be used to rigorously evaluate scientific hypotheses. The special session is going to include talks from these diverse areas and related research programs that advance the field of language research towards treating languages as evolving entities. And there's no more. And we have, towards this end, we have invited 9 distinguished speakers from all around the world, and those are, as listed, Morten Christensen, Michael Dunn, Maria Fedzeskina, Susan Golden Meadow, Adele Goldberg, Simon Kirby, Stephen Levinson, Emily Morgan, and Kaius Sinemaki. Some additional features of the conference that I want to draw your attention to. We have 3 poster sessions. There are 270 or 260 posters. Tonight, the first one is between 6 and 8:30 in a different building, which you can get directions to. It's our department's atrium. It's a lovely space, and there's food and drink provided, courtesy of your registration fees. So there's no drink tickets. There's just open bar. Don't overdo it. It's a long conference, okay? Oh, by the way, those of you who may remember the 2003 version of this conference at MIT in this very room, You may remember that I had to put bracelets on anyone who wanted a glass of wine or beer back then. Does anyone remember this? Was anyone here for that? Yeah, a bunch of people, okay. Remarkably, we have avoided this step this year. I think there's like some, I don't know why. But Jerry, I can still put a bracelet on you if you want. Remember Jerry, this was like an obsession that I had with putting on bracelets. Anyway, which also reminds me, we now have a code of conduct available on the website. So we want all of you to have fun and feel comfortable at our conference, at this community conference. So Jerry, if you want to complain about me harassing you, please talk to me or someone else. No, but so what? Talk to someone.
Everybody, man.
Okay, good, good. But kidding aside, we're actually very serious about the code of conduct.
I promise I'll behave.
Oh, okay, I was talking about me, not you. We also have 2 poster sessions on tomorrow and the next day for lunch. There's lunch provided, 12 till 2 in the same location, also covered by registration fees. And there's a post-conference reception with pizza and drinks, probably wine and beer on Saturday, also in that same area. And posters from Saturday will still be remaining up through that event. So basically, you are stuck with us, except for Friday night. Friday night, you can do what you want. Otherwise, you're with us. Okay, in addition to the reviewers, I want to thank a few other people. First of all, I want to thank my institution, MIT, which is a wonderful institution which has made much of this incredibly easy to host. They've paid for ASL translators. They've paid for captioning of YouTube videos that we are live streaming. So live streaming is going on, and there's captioning happening as we speak. And furthermore, there's many other benefits of having this. Well, for us, running MIT has been great. They have no restrictions on what vendors we've used to provide food or drinks. And they don't charge us for space. So this room is free, and the other space is free also to us. And so that allows us to pay for things like food during the poster sessions and drinks. Okay, these are marvelous benefits to an already great university. Second thing I want to thank is I want to welcome Roger Levy to our wonderful department, the Braden Cognitive Sciences. Is Roger here? Jeez. And I want to thank him for coming to join us here. To improve our department, that's right. So our gift, or my gift to Roger, is that he has done nothing in organizing this conference so far, but that's like, okay. Third, I want to thank my administrative assistant, Margot O'Leary, for organizing the stays of all the invited speakers at the conference hotel, which is a very non-trivial task. Fourth, I want to thank all the volunteers who are working downstairs out in the halls with the registration, coffee, food setup, etc. Those are Evgenia Diachik, Misha Ali, Matt Siegelman, Isabel Moore, Dima Ayesh, Brianna Pritchett, Zach Mineroff, Yingtong Liu, Zheng Zhang, Meilin Zhan, Jin Wu, Mika Brzezinski, Jaden Ziegler, and Sania Wyrak. And fifth, and most importantly, I want to thank the other members of the organizing committee for their leadership in organizing this conference. First, I want to thank Richard Futrell, who built the website, which is extremely non-trivial. Oh, thank you. Built the website and is dealing with all website issues throughout the conference. Second, I want to thank Melissa Klein. This is Richard. Can you stand up? That's Richard. He's going to talk. And then second, I'd like to thank Melissa Klein, who has taken upon herself to organize all the AV, all the audiovisual for the conference, which is an enormous amount of work, seeing as we are live streaming and recording for the first time. And we have an OSF site, as you probably know, for all posters and talks. Please upload your presentations as soon as possible. And we have ASL interpreters, thanks to Melissa over here, Melissa Klein. Third to Idan Blank, who designed the posters for the conference and the workshop and who built the app for the conference. Idan, do you want to say a few words about your app?
Sure, my app. The app that we use. So we have an application, I hope most of you know about this already. It's called Eventspace. You can download it to your smartphone and then you search for the event CUNY 2017, all lowercase. You have those short abstracts for every talk and every poster. You can search keywords or people you can mark, talks and posters that you want reminders about. And for all of the presenters that sent me info, you have their emails. For most of them, you have their personal or lab website, their Twitter handles, their Facebook pages, so that you can easily connect with one another. There is also a link from there to the Open Science Framework website with all the PDFs of the posters. And some maps of getting around and stuff like that. A link to recommendations of restaurants that we made. So download it and use it as is. Oh, and you can send me info if you want. I'm still updating it, so it's never too late to just send me more info.
Okay, thank you, Don. And fourth, to Rachel Riskin, who has organized all the reviewing process, which isn't a huge amount of work, and has organized many other things, including all the catering, which is huge, among other innumerable conference jobs. Thank you, Rachel. And finally, many of you saw our statement about the executive order that has been affecting scientists from several countries, in addition to others who are choosing to boycott U.S. scientific conferences. If you haven't seen this statement, I encourage you to look at our website and see the statement. We wanted to make sure, in answer to this, we want to make sure that this year's CUNY conference and workshop can reach everyone, and to test out some ways of making this conference an even better resource for the community. So we've done two things that you may be aware of. First of all, you may be aware, as I just mentioned, there's an online repository for talks and posters that's on OSF. And second, that device over there is a lecture capture camera, which is going to provide an online streaming version of the conference on YouTube, which is like some seconds delayed, but then also posted to a permanent site. This is the same. There's also an overflow room in case there's more than 425 people. Believe it or not, there are 425 seats in this room. It doesn't feel like it, but there are. And if you want to go there, there's an overflow room, which is, what is it, 333? 3333 in this building, is that right? Yeah, so it's like easy to find. Yeah, and it's connected. If you don't, for some reason, you want to work somewhere quietly there and watch, you can do that there. Okay, so I am pretty much on schedule. I would want to say the one thing's, if you want to keep that up to date on any questions, just use that hashtag on Twitter. Questioners, please be brief for short talks, and chess and chairs, I want you to be ruthless in moving on. What is the one thing? Oh, speakers, when you're speaking, you have to stay here because we have ASL over here and we're filming from there, so you can't have a mic and wander around. You're going to have to stay here. Okay, and I think that's all I have to say, and so we can get started 1 minute late. Rachel.
Okay, good morning. So it's my pleasure to introduce our very first invited speaker of CUNY 2017, Emily Morgan, who received a BA in mathematics in 2007 from Harvard, followed by a master's in brain and cognitive sciences from the University of Amsterdam in 2009. She recently got her PhD in linguistic and cognitive sciences from University of San Diego, where she worked with Roger Levy. Since then, she has been a postdoc at Tufts, working with Gina Cooper-Rigg and Anirudh Patel. Despite having completed her doctoral degree so recently, Emily's work has already had quite an impact on psycholinguistics. She has tackled questions about the interplay between experience-based expectations and the flexibility of language production by focusing on binomial expressions, and has developed a really thorough understanding of this domain by combining experimentation, corpus work, and probabilistic computational modeling, which she will tell us about today. Let's welcome Emily.
Thank you very much. So it's one of the hallmarks of human language that we have generative linguistic knowledge, which allows us to produce and comprehend novel utterances. And when I talk about generative linguistic knowledge, I'm talking about any knowledge that we can bring to bear when we encounter a novel utterance. So for example, we have syntactic and semantic combinatorial rules that allow us to compute meanings for novel utterances. But I'm also talking about things like violable constraints or probabilistic preferences. So for example, in the case of the dative alternation, we have a number of violable constraints on the elements of the noun phrases, such as their weight, their animacy, and so on, that would cause us to probabilistically prefer one structure over another. But in addition to this generative linguistic knowledge, there's also potentially a role for item-specific experience when we're processing non-novel utterances or utterances that we've heard before. So in particular, it's possible that we're able to store and directly reuse composite linguistic units. So for example, if I want to produce a past tense form like walked, it's possible that I generate this using a stem and an affix, but it's also possible, particularly for a high frequency form like walked, that I've stored this form and can reuse it directly. And of course, there are cases such as irregular verbs where we know we must be drawing upon our item-specific experience, because if I tried to generate this from a stem and an affix, I would get an incorrect form rund. Similarly, in the case of multi-word expressions, if I wanted to say something like bread and butter, you could imagine that I generate this from its component parts, or you could imagine that I've stored this as a holistic unit and can reuse it directly. And again, there are cases in multi-word expressions such as idioms, where we know we must be drawing upon our item-specific experience to understand these items, because if I tried to compute its meaning compositionally, I wouldn't get the correct idiomatic meaning. So the question I'm going to focus on today are, what are the roles of generative knowledge and item-specific experience in our language processing? To what extent is each recruited, and how does an item's frequency influence this balance? And in order to ask this question, we'll see that it's also helpful to ask a comparable set of questions about the structures that we see in natural language, namely, to what extent are these structures compositional versus idiosyncratic? And again, how does item frequency influence this balance? So to start just by thinking about the roles of these two knowledge sources in language processing, I'm going to make two uncontroversial assumptions. First of all, that language has both compositional structure and idiosyncrasies, and second of all, that people have finite language experience. So we can imagine a spectrum of items ranging from something novel or very infrequent up to something highly frequent, and imagine how these two knowledge sources might be deployed. So for our novel items, this is where we know we must be using generative knowledge. But what about the rest of this space? Well, one possibility is that we always rely upon our generative knowledge. But as we discussed before, we know this can't be true because of assumption number one. So there are irregular verbs, there are idiomatic expressions. We must be drawing upon item-specific experience to understand these. Another possibility is that we use generative knowledge only for totally novel items, and anything that we have any experience with, we rely wholly upon our item-specific experience. But this runs afoul of assumption number two, because not only do we have finite language experience, we sometimes have very limited experience with a particular item. And you can imagine if I use something that sounds like it's an irregular verb or an idiom that you've only heard one time before, you don't want to have total faith that you understand exactly how this item is being used. Maybe I produced it as the result of a speech error or some part of the discourse that you didn't understand. But as you have more and more experience with a particular item, you can be more confident that your experience is representative of how that item is actually used. So I propose that a rational solution would be to see a gradient trade-off between generative knowledge and item-specific experience as a function of the amount of experience we have with an item. That's the first claim that I'll be demonstrating for you today. Again, this is rational if we take these two assumptions into account. Now, assumption number two, that people have finite language experience, we can actually quantify very easily using the large corpora that are available today. But let's talk a little bit more about assumption number one. This isn't something we're in the habit of quantifying per se, although it's uncontroversial. So I'm actually going to show you a domain in which I think we can quantify the extent to which structures that we're seeing in natural language are compositional versus idiosyncratic. And the second claim I'll be making today is that we see another gradient trade-off in the structures of natural languages between compositionality on the low frequency end and idiosyncrasy on the high frequency end. So then, having told you something about language processing and how it's rationally motivated by language structure, I'm going to connect the dots by demonstrating how the gradient trade-off that we see in language processing could create and sustain the gradient idiosyncrasies that we're seeing in language structure. So in the rest of my talk, I'm first going to introduce you to binomial expressions, which are the test case I'm working with today, and then go through each of these three claims. Binomial expressions are expressions of the form x and y, and they're interesting in part because they have gradient ordering preferences. So for example, we prefer radio and television over television and radio in about a 63 to 37 ratio, but we strongly prefer bread and butter over butter and bread in a 99 to 1 ratio. And indeed, these preferences are reflected in our online processing. So for example, we know that a sentence like, George always brings bread and butter with him when he goes camping, is read faster than a sentence like, George always brings butter and bread with him. But what drives these ordering preferences? We can tell two stories. One story is that these preferences are driven by people's generative knowledge of violable constraints on the ordering of binomial expressions. For example, a preference to put the more frequent word first. And indeed, we know from corpus data that these ordering preferences are predictable from various semantic, phonological, and lexical features of the two words in the binomial. So under this story, if we're reading, George always brings bread and, when we get to this point in the sentence, we can use our violable constraints to make an online prediction about what's going to come next. For example, we would predict a less frequent word than bread to come next. When we get the word butter, that prediction is confirmed, and so it's read relatively quickly. In contrast, if we're reading George always brings butter and, at this point in the sentence, we'd be predicting a less frequent word than butter. When we get the word bread, that prediction is disconfirmed, and so it's read relatively slowly. But there's another story we can tell, which is that these preferences are actually driven by our item-specific experience. So under this story, when we're reading George always brings bread and butter, due to being a frequent unit, might be recognized and processed as a holistic chunk, and because it's a relatively frequent one, it's relatively fast to process. In contrast, when we're reading butter and bread, either that's not stored as a holistic chunk at all, and so we have to build it up compositionally, which might take more time, or it might be stored as a chunk, but because it's a lower frequency chunk, it's going to be slower to process. So the question that I want to ask first is, what are the roles of generative knowledge and item-specific experience in processing these expressions? So I'm going to tell you a little bit more about how we quantify these two knowledge sources for binomial expressions specifically. We can think of our item-specific experience with these expressions as having two components. One is the overall frequency of our experience, which we measure as the total number of occurrences of these two words together in a binomial expression in either possible order. This is something we can easily measure from corpus data just by counting up total number of occurrences. The other component of our item-specific experience is what I'll call the observed preference, which is how often in our experience we have observed one order as compared to another. Again, we can easily estimate this from corpus frequencies just by looking at the proportion of occurrences that occur in a given order. Now, when it comes to our generative knowledge of these expressions, we'd like to be able to express people's generative preference for one order over another, again, as something like a proportion between 0 and 1, corresponding to how strongly we expect people to prefer a given order for a binomial expression, just on the basis of their generative knowledge of violable ordering constraints, not on the basis of how often they've actually experienced it in one order versus another. So we can't estimate this directly from corpus frequencies because what corpus frequencies tell us about is our item-specific experience. So instead, we're going to build probabilistic models to estimate people's generative preferences. Now, of these three factors, the two that directly compete to explain people's preferences for a given expression are the observed preference and the generative preference, but the weight which each of these two factors plays might change depending on the overall frequency of the expression. So in particular, the prediction that I made before is that if we imagine a spectrum of binomial expressions ranging from something totally novel, like bishops and seamstresses, or seamstresses and bishops, through something of medium frequency, like facts and techniques versus techniques and facts, up to something highly frequent, like bread and butter versus butter and bread, we're going to see that there's a gradient trade-off between reliance upon generative preferences at the less frequent end to reliance upon observed preferences at the high frequency end. So my approach today is going to be to independently estimate the generative and the observed preferences and then compare their predictive power for behavioral data. Now at this point, I just want to very quickly point out that while the generative and the observed preferences for binomial expressions might be correlated, they're not going to be identical. So for example, in general, we have a strong constraint to put men before women, but our observed preferences for ladies and gentlemen strongly favor the opposite order. And I'm going to talk more later on about how and why these two types of preferences might diverge from each other, but for the moment, let's just take for granted that although they might be correlated, they're not identical. So now let me tell you a little bit more about the probabilistic model that we're going to use to estimate generative preferences. I'm going to start by telling you about 8 generative constraints taken from the previous literature that go into this model. The first is a formal markedness constraint, which says that words with more general meaning or broader distribution should come first. So for example, in boards and 2x4s, boards are a general class, 2x4s are a specific type. The perceptual markedness constraint says that elements that are more closely connected to the speaker should come first. This has a number of sub-constraints, including animates before inanimates, positives before negatives, and so on. For example, in attractions and repulsions, attractions are positive, repulsions are negative. The power constraint says that the more powerful or prioritized word should come first. For example, in clergymen and parishioners, clergymen have a higher rank. The cultural centrality constraint says that the more culturally central word should come first, as in oranges and grapefruit. The iconic or scalar sequencing constraint says that elements that exist in a sequence should be ordered in that sequence. For example, in breakfast and dinner, we eat breakfast first. The no final stress constraint says that the final syllable of the second word should not be stressed. So for example, because Japan has stress on the final syllable, we prefer to put it in first position. The frequency constraint says that the more frequent word should come first, as in bride and groom, and the length constraint says that the shorter word should come first, as in food and shelter. We combine these constraints using a logistic regression model, which means that we have a number of constraints, each of which may or may not be active for a given binomial. They're combined according to some weights, which produces an output which tells us the proportion of time that we expect a binomial to be realized in a given order. So for example, for a pair of words like bishops and seamstresses, we might have some constraints active which are combined according to their weights, and we predict that 86% of the time we're going to realize this expression as bishops and seamstresses as opposed to seamstresses and bishops. We created a corpus to train this model on by taking all of the noun and noun binomials from the parse section of the Brown corpus, hand coding them for all of these semantic constraints, and using the Google Books corpus to get very reliable frequency estimates. And then we can train and test our model using cross-validation. So just to briefly show you how well our model is doing, here on the x-axis, I'm plotting the true proportion or the observed proportion from a corpus of how often we see a binomial expression occurring in alphabetical order. I'm using alphabetical order as a neutral order because it doesn't influence people's binomial ordering preferences. So a 0 binomial is one that always occurs in non-alphabetical order, a 0.5 binomial is perfectly balanced, and a 1 binomial is one that always occurs in alphabetical order. And then on the y-axis, I'm plotting our model's prediction for how often, on the basis of generative preferences, we expect to see a binomial occurring in alphabetical order. And we see that our model is doing a reasonable job of predicting these preferences. If you're interested, you can ask me about other ways in which we've improved upon this model. For the moment, we're going to take this as our model of generative preferences, which means we can now test this prediction, asking how both generative preferences and observed preferences contribute to processing these expressions as a function of frequency. And I'm going to show you data today from a forced choice preference experiment. So we took 48 binomials spanning a range of overall frequencies from novel up to highly frequent, and we embed them in sentence contexts in both possible orders. So the violinist played with abandon and fervor, or with fervor and abandon during the concert, and we just asked people to choose which one sounds more natural. So I'm going to show you our results divided up into bins by frequency, starting with the totally novel items like boards and 2x4s or bishops and seamstresses that we don't expect people have ever heard before. So here on the x-axis, I'm plotting our generative knowledge model's prediction for how strongly an expression should be preferred in alphabetical order. On the y-axis, I'm plotting how frequently people actually choose that as the preferred order. And you can see here that indeed our generative knowledge model is predicting people's preferences. So these generative ordering constraints do apply when people are processing novel items. We've replicated this with a much larger set of items. So now I'm going to go on to show you the rest of our items divided up into low, medium, and high frequency bins. So here I'm plotting something different. On the x-axis, again, I'm plotting our generative knowledge model's prediction for how strongly an expression should be preferred in alphabetical order. Now on the y-axis, I'm plotting the observed preferences taken from corpus data. So where an item is located on this graph tells you something both about its generative and its observed preference, and the point shading tells you how often people actually preferred it in alphabetical order. So a lighter shaded point is one that people tend to prefer in non-alphabetical order, and a darker shaded point is one that people tend to prefer in alphabetical order. So now, since I'm in 2 dimensions, instead of plotting a best fit line, I'm plotting a best fit gradient, which means that lighter points on this space are points where people tend to prefer expressions in non-alphabetical order, and darker points on this space are points where people tend to prefer the expression in alphabetical order. And what we see here for these low frequency items is that there's a very strong horizontal gradient, indicating that as generative preferences are changing, that is strongly driving people's actual preferences to change. To a lesser extent, there's a bit of a vertical gradient, so there's also some contribution here coming from the observed preferences. Now, if we go on to look at our medium frequency items, again, I'm plotting generative preferences on the x-axis and observed preferences on the y-axis, and here we see a strong diagonal gradient. So both as generative preferences change and as observed preferences change, both of these are driving changes in people's actual behavior. Finally, if we look at our high-frequency items, we see this very strong vertical gradient, indicating that preferences for these items are being driven pretty much exclusively by the observed preferences. So if we look across all of our items, we see this change in the gradient from mostly horizontal through diagonal up to vertical, indicating that there is this gradient trade-off in processing between reliance upon generative preferences at low frequencies and reliance upon observed preferences at high frequencies, which supports my first claim. Another way of thinking about this is we can think about generative knowledge as serving as a prior. It's our best guess about how an expression is going to behave before we have any data about it. Then the item-specific experience serves as data, and the more data you have, it can gradually come to overwhelm your prior. Now, as I said in the beginning, this is rational if binomial expressions have both compositional and idiosyncratic preferences. So the next question I want to ask is, how idiosyncratic are binomial ordering preferences? And moreover, how are these idiosyncrasies distributed? That brings us to part 2. So I'm going to define a binomial expression as being compositional to the extent that its observed preference conforms to its generative preference, and idiosyncratic to the extent that its observed preference differs from its generative preference. So for example, if I think about an item like girls and boys or boys and girls, which has a generative preference of 62 to 38 and an observed preference of 88 to 12, I can say that this expression is somewhat idiosyncratic to the extent that the observed preference differs from the generative preference. But of course, what I'm interested in most is not how idiosyncratic any one item is, but across the language as a whole, how are these idiosyncrasies, how do these idiosyncrasies manifest, how are they distributed? So one way we can start to ask that question is by looking at the language-wide distribution of preferences. So we can start by looking at the way generative preferences are distributed. And what we see is that our generative preferences predict a very nice unimodal distribution, where we expect we're going to have a lot of very balanced expressions, a lot of expressions like radio and television or television and radio that you could use rather well in either order, and not a lot of expressions at the extremes like bread and butter or ladies and gentlemen that are strongly preferred in one order. So what do we see in the observed preferences? Well, here we see something very different. We see a multimodal distribution where in addition to having a lot of balanced expressions, we also have a lot of very polarized expressions like bread and butter and ladies and gentlemen. Another word for these expressions is regularized, meaning that they're preferred more strongly in a single direction, or they have preferences close to 1 and close to 0. I quickly want to point out this is a different notion of regularization than when, for example, we talk about a regular verb in morphology. So this is a notion of how consistently an expression is being used in a single direction. So we've seen that there is a lot of idiosyncrasy. In particular, there's a lot of regularization in the observed preference distribution that's not predicted by our generative preferences. So which items is it that are tending to become most idiosyncratic and in particular most regularized? Well, I predict that again we're going to see a gradient trade-off wherein less frequent expressions are behaving more compositionally and more frequent items are behaving more idiosyncratically. And I'm justifying this in 2 ways. First is by analogy to morphology, where we know that high-frequency verbs, for example, are more likely to behave idiosyncratically, but also as a result of the gradient trade-off that we saw in part 1, where these novel expressions are being processed primarily with respect to generative knowledge, and so almost by definition, they must be behaving in a way that conforms to their generative knowledge. Whereas the more frequent an item is, the more it's being processed with respect to our item-specific experience, which means that there's a possibility for idiosyncrasies to be introduced and to persevere. So one simple way we can test this is simply by plotting that measure of idiosyncrasy that we defined before as a function of the overall frequency of an expression. And indeed, we see that as binomial expressions become more overall frequent, so as 2 words occur together more frequently in a binomial, their preferences do tend to become more idiosyncratic. And we can again check that this idiosyncrasy is taking on the form of regularization by defining a measure of regularization, which is simply how close to 50-50 versus how close to the extremes a binomial preference is. And again, we see that regularization is increasing as overall frequency increases. So in other words, as predicted, the observed preferences for binomials with higher overall frequency are deviating more from their generative preferences, and they're deviating in a specific way, which is to become more regularized. And this is a phenomenon that we call frequency-dependent regularization. And it supports our second claim that binomial expressions are gradiently idiosyncratic as a function of frequency. So finally, I want to ask, how does this pattern emerge diachronically? So first, let's talk very briefly about what we know about the phenomenon of regularization. This is a well-established phenomenon in statistical learning tasks, although the factors that lead to regularization in some cases and not others are really not very well understood. And it has been hypothesized to be potentially an important mechanism for language change. But regularization is not known to be frequency-dependent. Such frequency-dependent regularization has not been empirically demonstrated. It's not predicted by theoretical accounts of regularization, and it's not predicted by standard iterated learning models of language change. I'll show you an example. In a classic regularization experiment by Reale and Griffiths, subjects are exposed to two labels for a novel object. They might hear this object called a mech 6 times and a dit 4 times. When they're then tested on labels for this object, on average, they reproduce the more frequent label even more frequently than it was seen in training. This is a classic regularization finding. However, this regularization is not known to be frequency dependent. So in particular, whether people have seen 10 total labels in training or 100 total labels in training, the amount that they regularize is not predicted to differ. So this is the way in which regularization is not known to be frequency dependent, which means that there's really a puzzle. How does the frequency dependent regularization that we saw in our corpus data emerge for these binomial expressions? And my proposal is that this emerges via the interaction of an individual cognitive bias for regularization with the process of cultural transmission. And I'm going to demonstrate how if a frequency-independent regularization applies at the level of individuals, we can actually see frequency-dependent regularization emerging over time. I'll demonstrate this using iterated learning models. The way these models work is that we have a speaker who, for a given pair of words, has some hypothesis about how often they should be used in a given order. That speaker produces some data, which is heard by a speaker in the next generation, who has to combine that data with their prior knowledge to form their own hypothesis, generate their own data, and this process continues iteratively. And this allows us to ask questions like, in the long run, what does the distribution of hypotheses look like? So in a little bit more detail, the type of model that I'll be working with today, a speaker has a hypothesis theta for how often a given binomial should be used in a particular order. They're going to produce n tokens, of which x1 are in alphabetical order. This is going to be distributed binomially, meaning that we have a coin which comes up heads theta% of the time. We flip that coin n times, and however often it comes up heads, that's how often we're going to say the binomial in alphabetical order. The speaker hears that data and needs to come up with their own hypothesis. On the basis of our results from part 1, we know that they can use their generative knowledge about this expression as a prior and their item-specific experience as the data, and Bayes' rule tells us how to combine the prior with the data likelihood in order to form a new distribution over hypotheses. Specifically, this data likelihood term is just given to us by the binomial distribution, but really quickly, let me tell you about how we're going to formalize this prior over hypotheses. We're going to do that using the beta distribution, which is a distribution over the interval from 0 to 1 that has two parameters. One is a mean, which tells us what the mean of the draws from this distribution are going to be. And the other is a concentration parameter, which tells us how tightly clustered around the mean draws are going to be. So for example, with a relatively low concentration parameter, draws from this distribution are going to be relatively spread out, whereas with a relatively high concentration, draws from this distribution are going to be more tightly clustered around the mean. So in order to set a prior for a given binomial expression, we're going to set mu, the mean, to be the generative preference, because that's our best guess for how this binomial should behave before we have any experience with it. And nu is going to be a free parameter in our model because we don't know how to set it a priori. So we can now combine our prior and our data to form a new distribution over hypotheses, sample from it using any of the standard methods. And the first thing I want to show you is that this standard iterated learning model does not predict frequency-dependent regularization. To do that, I'm going to model the evolution of a single hypothetical binomial expression, which for the sake of argument is going to have a mean of 0.6. And we're going to vary n, we're going to vary the number of times that this binomial is seen by a speaker in each generation. So the crucial question is, does the regularization vary with the frequency of experience in each generation? To do this, we run some large number of chains of speakers for a long number of generations and look at the resulting distribution over hypotheses. If we do that, we see here that regardless of n, this distribution is not changing much. In particular, it's not becoming closer to 1 or closer to 0. So regularization is not frequency dependent in the standard model. So we're going to introduce an augmented model with a frequency independent regularization bias that applies during data generation. The way this works is that a speaker forms their hypothesis just like before, but then they apply a regularization bias to produce a new hypothesis theta prime and produce data from this new hypothesis. So what does this regularization bias look like? Well, we want it to look something like this. We want to take values of theta and push them closer to 0 and closer to 1. The function that we're going to use for this is the regularized incomplete beta function. What that means is that we have a function with one parameter alpha, which controls how curvy the function is. So when alpha equals 0, this is just the identity, and theta prime is equal to theta. But as alpha gets larger, this function gets more curvy. So values of theta prime are getting pushed closer to 0 and closer to 1. So now we can ask, does this augmented iterated learning model predict frequency-dependent regularization? And we'll do that by running the same simulation, this time using a small but non-trivial regularization bias. And if we look at the results here, we see that in the augmented model, as n increases, we do see the peak of this distribution moving closer to 1 and closer to 0. So in other words, regularization is frequency-dependent in the augmented model. So how does this come about? Well, we've seen that we introduced a frequency-independent regularization bias, but we saw frequency-dependent regularization emerging. And the reason this can happen is because there's a tension between the prior, which is to say generative knowledge on the one hand, which is favoring these denser distributions, and people's item-specific experience, which now includes a regularization bias. And this tension is mediated by expression frequency. So at low frequencies, there's not enough data for the regularization bias to overcome the prior, and so the resulting distributions indeed look a lot like the prior distribution. But at increasingly high frequencies, there's increasingly enough data for this regularization bias to be magnified across generations. And this is what's known as the bottleneck effect of cultural transmission. We've also seen that even a quite weak bias can produce regularization when it has the opportunity to compound across generations. So the last thing I want to show you is going back to our initial puzzle, which was specifically how does this corpus distribution of observed preferences come to differ from the generative preference distribution? So in particular, can our model with this augmented iterated learning model with a regularization bias actually predict the distribution that we're seeing in the observed preferences? In order to do that, I'm going to model our entire corpus. So for every binomial expression in our corpus, I'm going to set mu to be its generative preference, and I'm going to set n to be the actual number of times that we expect a real average speaker to have heard this binomial in their lifetimes. And again, we can simulate the distribution over all of these binomial expressions by running some large number of chains for a large number of generations. Again, we have two free parameters in our model. As discussed before, we have a nu parameter which controls the strength of the prior, and an alpha parameter which controls the strength of the regularization bias. And I'll show you what happens when we run the simulation at different settings of these parameters. So here are the results at different parameter settings. What we see is that in cases where we have a weak regularization bias and a strong prior, indeed the resulting distribution looks a lot like the prior, it looks a lot like our generative preferences. In cases where we have a weak prior and a strong regularization bias, we see far too much regularization occurring. But in cases where the regularization bias and the prior are appropriately balanced, we indeed see that our model is predicting the same sort of multimodal distribution that we see in the true observed preference distribution. So in other words, we've seen that this augmented iterated learning model with a frequency-independent regularization bias nonetheless predicts emergent frequency-dependent regularization due to this tension between the prior and our item-specific experience, which now includes a regularization bias, being mediated by the bottleneck effect of cultural transmission. And moreover, that this can predict the actual observed preferences that we see in corpus data. So this supports our third claim, which is that the gradient trade-off that we saw in language processing, plus this regularization bias, can create and sustain the gradient idiosyncrasy that we're seeing in language structure. So to summarize, today I showed you, first of all, that processing of binomial expressions relies gradiently upon generative and item-specific knowledge as a function of item frequency. Second of all, that this is rationally motivated by the fact that binomial expressions are gradiently idiosyncratic, in particular becoming more regularized as a function of frequency. And third, that expression frequency can serve as a bottleneck effect in cultural transmission, such that the facts of language processing can create and sustain the facts of language structure. Or in other words, I've shown you that these two gradient trade-offs are mutually constraining, such that studying language processing and language evolution simultaneously can actually give us a much more cohesive picture than if we only looked at one facet or the other. To conclude, I want to thank all of my collaborators, particularly Roger Levy, Wednesday Bouchong, and Melody Yen, who have helped a huge amount with this work, and thank you all very much for listening.
Hi, Mary Ellen McDonald, University of Wisconsin. This is really, really interesting. I have like 6 questions, and I'm going to choose the one that asks you about the relationship to what you call generative versus item-specific, because many of those generative rules, like the syllable structure or the animacy and all of that, are themselves gleaned from observation over items. And so I guess maybe in the interest of time, I'll say it in the pushy way, isn't this artificially creating some distinction between the observational learning and the rule-based generative approach there?
You know, I think that's a really great question, and I think to a large extent that's actually still an empirical question. So definitely I have drawn a line here where I've said that some knowledge is generative and some knowledge is item-specific. And I think there's a reasonable diagnostic we can use to decide what knowledge is generative, specifically that generative knowledge has to be able to be applied to novel utterances. So we have demonstrated that these violable constraints on ordering are generative in that sense. But you're absolutely right that our generative knowledge, to some extent, possibly to a very large extent, is learned from our item-specific experience. And I think it's an open question when we're actually storing and representing these types of knowledge, to what extent are the generalizations themselves things that we have pre-generated? So to what extent have I as a speaker, pre-computed the abstract rule that I need to put the more frequent word before the less frequent word, or that I should put the more culturally central word before the less culturally central word, and to what extent is that generalization itself something I can generate on the fly in a more exemplar model type fashion? So when I go to produce a specific expression, to what extent am I directly analogizing to other exemplars? And that, I think, is an open question.
Scott Frondorf, University of Pittsburgh. So as you were presenting your examples, one of the things that I was thinking about is Horn's principle. So if you express things in sort of an unconventional way, it means an unconventional meaning. So you can say, if you say, I had bread and butter for breakfast, that sounds like the conventional way you put your butter on the bread. Whereas I was imagining if somebody said, I had butter and bread for breakfast, to me the reading I sort of get from that is that they had a breakfast that involved butter and bread, but maybe not in the conventional way. Like they just had some butter, a slab of butter, and then they had some bread. So I was wondering, is that something that can be incorporated into your story? Is that consistent with this model, or is that sort of something that's not incorporated in the model?
Yeah. So yes and no, I think. There's sort of 2 ways in which we can think about this operating. So one way in which we can think about this operating is it fits very naturally within this story. So for example, if I say something like, I had butter and bread for breakfast, maybe it means that the butter was actually a more central part of my meal. So I ate a lot of butter with a little bit of bread on the side. And I think that fits very naturally within this story. There's sort of a second layer of inference that you might put on top of this, which I don't know if butter and bread is the most striking example of it. If I said something about gentlemen and ladies instead of ladies and gentlemen, something that sounds very, very marked, the fact that you might sort of do an extra step of inference to infer that I mean something very different than what I would otherwise mean with ladies and gentlemen. And I don't have any evidence. I've sort of just, in my daily life, anecdotally, tried to kind of listen for people doing this type of thing, and I haven't noticed it happening. That's not to say that it doesn't happen, but yeah, so I think there's sort of two different ways in which that can work, one of which fits very naturally within this story, and one of which might require some extra inferences.
Cool, thanks.
Frank Keller, Edinburgh. So you have given us a very interesting story about the representation of these generative constraints that are involved in binomials and also about how they're being acquired in your iterative learning model. I was wondering, though, about the online processing of binomials. If you could speculate a little bit on that, because as a listener, if I have a binomial coming in, I need to process it incrementally, so I don't know the second aspect yet, the second part of the conjunction yet when I'm processing the first one. So how would you imagine these constraints are being deployed online?
Yeah, so I think actually our existing processing theories actually fairly straightforwardly can represent the types of processes that I'm talking about here, as long as our processing theories assume that we can store larger units. So in particular, any sort of tag or any sort of fragment grammar, you could imagine that we both are capable of structurally generating bread and butter using compositional rules, or we have some larger tree structure which already has bread and butter as its terminals. And as long as we're able, so if I'm listening and I'm hearing bread and, as a listener, as long as I have both of these represented with appropriate frequencies, I can marginalize over whether I'm hearing something that's been generated or whether I'm hearing a larger unit, and therefore appropriately predict the probability of butter coming next.
And what would happen for novel binomials that are not lexicalized in your tag lexicon or something like that?
Oh, I see. So the question is, how do the generative constraints get into this process? Yeah. So, I mean, within this story, you do need to include that when you're generating these things compositionally, you do need to be taking into account these generative constraints in order to decide what the appropriate probabilities for the second conjunct in your generated structure are. Yeah.
Okay. Tal Lindsay and Nicole Montefiore, Paris. So where does the regularization bias come from? Why is that a rational thing to assume?
That's a fantastic question. I have a lot of possible answers and really no evidence for any of them. So one possibility is that this is actually a much broader cognitive property, and that it's just something about how we represent probabilities that are not even necessarily linguistic, and that's just some cognitive property of being a human. Another possibility is that the regularization bias is being introduced by properties of language use that the listener doesn't necessarily have access to, and therefore sort of can't undo, so to speak. So for example, it could be the case that when two people are conversing, they tend to settle upon a form, which might lead to the appearance of regularization in the listener's experience, but that the listener doesn't have access to the full history of that conversation, and therefore doesn't understand why there was sort of extra regularization occurring in this context, for example. There's a little bit of evidence showing that that might be the case. More generally, it could be the case that, so another way of sort of phrasing this question would be to say, okay, if it is the case that regularization is occurring for whatever reason, why can't a rational listener sort of undo that? Hear what they've heard in their language experience, but understand that it's coming from a somewhat regularized distribution. And so a third story would be that listeners are trying to undo this regularization, but they have uncertainty about exactly how much regularization is occurring, and so their undoing process ends up not fully undoing all of the regularization that has happened. All of these stories rely upon the fact, which I think is a true fact, that even very small amounts of regularization in any particular individual or any particular generation can have this compounding effect in the long term.
Mm-hmm. All right, thank you.
Thank you.
Richard Futrell. Hi all. So today I'm going to introduce a new model of difficulty in sentence processing called noisy context surprisal. And I'll present arguments that this can capture some interesting phenomena from the sentence processing literature. So first I'll explain the idea. So surprisal theory is the idea that the sentence processing effort at a word is proportional to the information content of that word in the context. This is just saying that very generically when we get a word, we do Bayesian updating on our posterior beliefs about the sentence, and surprisal is just a measure of the magnitude of that update. And it's calculated as the negative log probability of the word given the context. So the way this works in an example is, imagine I'm reading a sentence like this, word by word. We think that the processing effort at the word the is going to be proportional to the negative log probability of the given the beginning of the sentence context. Then the processing effort at the word troops is going to be related to the probability of troops given the. Processing effort at attacked is going to be negative log probability of attacked given the troops. And then at the word by, we might expect a lot of slowdown because probabilistically, we're more likely to expect troops to be attacking something than for them to be attacked by something. So we're likely to expect a lot of processing slowdown here because of surprisal theory. And we go on reading the sentence word by word in that same way. Now, there's a large class of processing difficulty effects which surprisal models don't capture. These are dependency locality effects. These are observed processing difficulty when words linked in a syntactic dependency are far from each other in linear order. So as an example of dependency locality, consider these sentences with some phrasal verbs. So we can say, John threw out the trash. That's a fine sentence. It's acceptable, so I'm going to give it a thumbs up. And we can see a dependency exists between through and out. So when you're reading through this, you're going to have to integrate your representation of the word out with your representation of the word through to get to the meaning. We can also say John threw the trash out, so there's variation in where we can put the particle in English. We can say John threw out the old trash that had been sitting in the kitchen. But now this version of the sentence, John threw the old trash that had been sitting in the kitchen out, this sounds kind of weird and awkward. And we think part of why this sounds bad is that there's a long dependency between through and out. So when you're incrementally parsing this thing, when you get to the word out, you have to try to remember the word through, which you saw earlier. But that memory retrieval operation might be difficult or inaccurate. And the length of the dependency corresponds to the amount of time that you had to keep that representation of through in memory. And we think that retrieval might be more difficult or more inaccurate the longer it's been in memory. And so we observe reading time slowdowns at these sites, and this sentence is less acceptable than the rest. So dependency length corresponds to difficulty or inaccuracy of retrieval. And this idea of dependency locality as a measure of sentence processing cost has been used to explain a lot of phenomena, such as difficulty of multiply set or embedded clauses and asymmetries between processing subject extracted and object extracted relative clauses. So we're left basically with two kinds of theories. There's surprisal, which is fundamentally based on probabilistic expectations, and there's memory-based models like dependency locality, which are fundamentally based on these sort of mechanistic parsing models. Usually these are combined as what effectively ends up being two factors in a multifactorial model. But that ends up missing out on some of the interesting phenomena that exist at the intersection of memory constraints and probabilistic expectations, such as structural forgetting, which I'll be talking about later. The goal for this talk and this theory is to combine surprisal with memory constraints at the computational level. So to do this, we're going to take our inspiration from noisy channel models of sentence comprehension. So it's known that humans correct perceived errors in the linguistic input they get. So if you hear the sentence, the mother gave the candle to the daughter, you're unlikely to think that the speaker intended to actually convey the literal meaning of this sentence, which is that a daughter was given to a candle. You're more likely to think that the speaker actually wanted to say the mother gave the candle to the daughter. And maybe the speaker misspoke, or maybe you missed the word to, and some noise process basically corrupted this sentence from its original intended form to the form that you got, which was lacking this word to. Now in general, when we're comprehending language in this way, considering possible noise, we do that by considering the possible intended messages that gave rise to the received message we got. and we assign to each hypothesized intended message a weight, which is proportional to the probability, the prior probability of that intended message, times the probability that noise would have corrupted that intended message into the thing that we actually got. So the basic idea here is we're going to apply this same principle to memory. So recall that in surprisal theory, cost of a word is the negative log probability of a word in context. Let's think about how we would handle an example like this in surprisal theory. So we think there's difficulty at out because it's really far from its dependency with through. No surprisal theory, as it currently exists, is going to explain this difficulty because surprisal theories are based on perfect knowledge of context. There's no room for forgetting or retrieval difficulty, and our goal is to build that in somehow. The way we're going to do that is to suppose that the memory representation that you're using to predict the next word is noisy. So we see here that context is noisy. Maybe when the comprehender is understanding the sentence, she doesn't remember the exact words that were said. She has a noisy representation of context and is trying to form. Now, when the comprehender with a noisy representation of context is trying to form expectations about what's going to come next, she's going to do the noisy channel thing and think, what were the possible true contexts that gave rise to my noisy representation? And so she's going to consider possible hypothetical true contexts, such as maybe she'll think it was, in fact, John threw the old trash bin sitting in the kitchen, the correct one, and that predicts out. Or maybe she'll think it was actually this, John removed the old trash bin sitting in the kitchen, in which case you would not predict out. Or maybe she'll think it's this, in which case, again, you would not predict out. So you see that some of these predictions, some of these possible contexts predict out, and some of them don't. So now the way that we say that the comprehender is going to predict the next word is going to be to integrate over all the possible intended, the possible true contexts, weighting by their prior probability and the probability that you got the noisy context given the true context. And we're going to say that the expected processing difficulty at a word is just it's the average over all the possible noisy contexts given the actual true context. So the actual noise model here could be anything. I'm going to use some very simple noise models in this talk so we can derive some sort of first order generalizations, but the real best noise model in this context is yet to be determined. And the noise model is where you could put things such as similarity-based interference, although I'm not going to be getting into that in this talk. So that's the theory. Now I'm going to show how we can derive dependency locality effects from this model as a subset of a more generalized kind of locality effect, which we predict, called information locality. So let's take a closer look at the structure of this example. We think the crucial context for predicting the word out was really the word through. Now suppose that the amount of noise increases the longer a word has been in context. Something like this. So I'm assuming a very simple naive noise model here as a first order approximation, and we think that the generalizations we get are going to apply to more sophisticated noise models and memory models as well. So now in this setup, since through is far away from out, it's very likely to be affected by noise and then corrected to something else which might not predict out, which means that when we get to out, it's going to be more surprising. On the other hand, if through is closer to out, it's less likely to be affected by noise, it's more likely to be present, and it's more likely to make that word out more predictable in context. So the basic generalization here is that noisy context appraisal increases when words that predict each other are far apart. And this is the principle that we call information locality. I've showed this here in an example, and next I'm going to show how this follows more generally from the noisy context appraisal model. So as a simple starting point, we take a noise model where we just erase words probabilistically with some probability that increases the longer a word has been in the context. When we do that, it turns out that as an approximation, we can say that the noisy context appraisal of a word is its inherent surprisal out of context minus the sum of the pointwise mutual information values with all the words in the context, the extent to which each word in the context predicts the word, weighted by the probability that those words survived the erasure process, the noise process. So I'll work that out in an example here. We're interested in the processing difficulty of out, given John threw the trash. We start by calculating the information content, the surprisal of out of context. So this is this blob of information, that's the information content of out of context. We subtract the pointwise mutual information with the word John, which is the extent to which John predicts the word out, weighted by the probability that the word John was not erased. Subtract the PMI with through, weighted by the probability through is not erased, and so on for the other words in the sentence. Now there's two things to note. First, I've assumed that the surprisal reduction due to each word in the context doesn't overlap here. That's not entirely true. That's exactly why this is just an approximation. But if you check out the paper that I'll cite later, we show that the error introduced by this approximation is bounded. Second, we note that we think most of the surprisal reduction at the word out is just because of this word through. So that's the biggest chunk there. So going forward, let's just assume that through is the only informative context for predicting the word out. And now let's think about what happens as this word through gets far away from out, as it gets farther back in the context. What happens is, as this moves to the left, the probability that it's going to be erased increases, and so its surprisal reducing effect here decreases. And this is just information locality. When context items are far away, their cost reducing influence decreases. And this ends up converging with a similar concept of decay and queue effectiveness that's been suggested in previous work. So now we've gotten to information locality, the idea that there should be processing difficulty that happens when words that predict items, that context items that predict each other are far apart. I've been promising this has something to do with dependency locality, but these are logically independent things. There's no reason that two words that are in a syntactic dependency in any particular sentence should happen to predict each other more than any other pair of words. These things are related, though, under this linking hypothesis, which is that words in syntactic dependencies have the highest mutual information. They happen to be the words that predict each other the most. This assumption is actually completely ubiquitous in practical models that are used in natural language processing, but it's never been tested directly. If it's true, we can see dependency locality effects as just a subset of information locality effects, because those words in dependencies are just those words that predict each other. So what I'm going to do now is show that this linking hypothesis is true in dependency corpora of many languages. So to test that words in dependencies have high mutual information, I'm going to compare mutual information of words in direct dependencies, schematized here as a head and its dependent, with words in other kinds of dependency relationships. So we can consider words, two words where the first word is the head of something, which is in turn the head of the second word. Or we consider words two words that are siblings, both dependents of the same head. And for each of these kinds of syntactic relationships in a dependency corpus, I'm going to calculate the mutual information, the extent to which the words predict each other, in this case over part-of-speech tags. So concretely, we're asking, given words in a direct dependency relationship, if I found out the first one's a noun, how much does that reduce my uncertainty about the other part of speech? Or if I find out here the first thing is a noun, how much does that predict the part of speech of the second thing in this pair? And so on. Now I'll show results for dependency corpora. I'll show 3 bars in each facet here. So red is direct dependency relationships. We think those are going to be the ones that predict each other the most. And blue and green are these other kinds of syntactic relationships. It turns out that across all languages that we tested in the universal dependencies corpus, very robustly, the words that predict each other the most happen to be those that are in some direct syntactic dependencies. So we derived this principle of information locality that we showed generalizes dependency locality effects, getting a result that converges with previous ideas such as decay and queue effectiveness. And this was derived from a general theory of language understanding as a rational inference with limited memory resources. Finally, I'm going to show our model can account for structural forgetting, which is an interesting, a puzzling phenomenon at the intersection of probabilistic expectations and memory constraints. So I'll show the phenomenon here. Here's a sentence. The apartment that the maid who the cleaning service sent over was well decorated. Now this sentence is complicated and it's hard to understand, but many people find that it sounds more fluent and more natural than this sentence. The apartment that the maid who the cleaning service sent over cleaned was well decorated. So this will typically score higher than this on acceptability ratings, so I'll give this a thumbs up and this a thumbs down. But you might notice that the first sentence actually doesn't make any sense. The maid here, this noun phrase has no verb phrase. It's a subject noun phrase. There's no verb phrase corresponding to it. So here's a nice well-behaved parse tree for the second sentence, which is grammatical, although it sounds bad to native English speakers. Here's a parse tree For the first sentence, the best one I could come up with, we see there's a missing verb phrase. So something happened here. This was forgotten. So this effect is called structural forgetting. It's the effect where you forget part of the beginning of the sentence, and that means you make the wrong predictions about the end of the sentence, and you get a grammaticality illusion out of it. So this might seem puzzling, but in fact it's even weirder than that. Although this effect has to do with memory, which we usually like to think of as a sort of fixed resource across speakers of different languages, the effect is language dependent. So in German, native German speakers find that this sounds better than this. They don't have the grammaticality illusion. They don't have the structural forgetting effect. Which raises the question, what's the relevant difference between English and German, such that this difference obtains? It's probably not that Germans have better memory in general. So the only existing fully formal explanation for this is Stefan Frank showed that a recurrent neural network trained on English text gives higher probability to the first sentence in English than to the second sentence. So it sort of reproduces the grammaticality illusion. But that raises the question of what aspects of the neural network structure give it that behavior. So we're going to explain this using noisy context surprisal. And the basic thrust of the explanation is that these kinds of contexts, the apartment that the cleaning service who, these are just more common in German than in English. And in noisy memory undergoing this kind of noisy channel correction, more probable things are more likely to survive that error correction process than less probable things. So the reason we think these contexts are more common in German than in English has to do with the way relative clauses work in the two languages. So in English, most relative clauses are SRCs, 80%, according to Roland et al., and the rest are not. SRCs are often verb initial, and ORCs are often verb final. In German, on the other hand, whether you're an SRC or an ORC, it's always verb final. So these contexts that build up nested verb final relative clauses have to be more common in German than in English, because that's all the relative clauses in German. Now, structural forgetting means that the ungrammatical sentence is easier to process than the grammatical one. That's how we're interpreting it. So this is the relationship of processing cost. The ungrammatical sentence has less cost than the grammatical one. If we schematize this and look at it in terms of only parts of speech, we see that the crucial difference is that the ungrammatical sentence has 2 verbs at the end and the grammatical one has 3. So we're going to say that we can model structural forgetting in principle when an ungrammatical sentence with 2 verbs comes out as less costly than a grammatical sentence with 3 verbs. So starting with this kind of prefix, we apply noise. And then we try to correct that noise based on our prior about the language. So for German, we're often going to correct this noise to things like this, which are correct, which involve nested verb final relative clauses. And that correctly predicts a 3rd verb. Whereas in English, we're more likely to correct it to something like this, which is like the noun, that verb, that this is a SRC context. This verb initial thing is not possible in German. Given this correction, you incorrectly predict that the sentence should just end after 2 verbs. So we tested this using toy grammars of the domain of nouns and their post modifiers before verbs in English versus German. And I'm going to skip through this. That's the grammar. You can ask about this in the questions. It's basically a probabilistic context-free grammar over these part of speech tag sequences for nouns and relative clauses before verbs. So when we take those grammars, we can simulate English and German, the difference between them, by taking the same grammar, except for German, we set the verb final relative clause rate to 100%, so all of the relative clauses are verb final. And in English, we set that to 20%, so only 20% of the relative clauses are verb final. When we do that and plug that into the noisy context surprisal model, we get a surprisal differences that match the observed structural forgetting effect. So this plot is going to show surprisal differences from the ungrammatical thing to the grammatical thing. So when the ungrammatical thing is less costly than the grammatical thing, it's going to be negative. And when the ungrammatical thing is more costly, then this value is going to be positive. And when we do that, we find a negative effect for simulated English. And we find a positive effect corresponding to no structural forgetting in simulated German, where the only difference between simulated English and German here is this verb final relative clause rate in the grammar. So now I'll compare these results to some reaction time data from a previous experiment that was studying these phenomena. So here I'm comparing to reaction time differences, again, from the grammatical to the ungrammatical. These are ungrammatical and grammatical completions of the sentence after the verbs. So the model can capture structural forgetting effects in principle and the language dependence of them. And it does it through the principle that the probability that context is remembered correctly just depends on its prior probability according to language statistics. I think this model actually explains the behavior of the recurrent neural network from previous work. We can see RNNs as predicting words given a lossy representation of the context, and that's analogous to the noisy representation of the context that I presented here. And the model also nicely resolves this grammaticality illusion in a way that includes an explicit grammar which is just not applied quite correctly. So, to summarize, I presented a unification of surprisal and memory-based models that derives dependency locality, and I showed that this can capture structural forgetting effects in principle and language dependence in those effects. Finally, to conclude, I'll lay out what I think is the main prediction of this model, which we're testing and which maybe I can entice you to test, which is that dependency locality effects are modulated by the mutual information of the two words involved in the dependency. In the future, we're going to work on integrating more sophisticated memory models into this, for example, the Anderson and Schuler model and also similarity-based interference, and that can all be modeled via the noise model. Overall, I think this noisy context appraisal thing, it provides a nice general framework for thinking about predictive processing with lossy context representations. That's it. Thanks all.
So this is really neat work. I had a question. This seems obvious, so I feel like somebody's done it, probably Roger, but another way one can try to capture the same sort of memory effects, it seems, or the problem you're worried about in part is that we're doing sort of batch inference, right, over all prior information we have, and you're getting rid of some of that by forgetting. Another way of having forgetting is using a particle filter, which would also get increased forgetting the further back it is, and also have the, you'd be more and more likely to forget lower probability options. A, has that been done, but B, does it give different predictions than what you have here? I mean, you might see it as just like an algorithmic variant of what you're suggesting.
So I think what that would end up doing, yeah, I see what you're saying. So that's actually the kind of logic we initially had in mind when we set up this model, and it corresponds to a particular kind of memory decay. So I think that the results of a particle filter could be modeled. Yeah, I think that's basically an algorithmic implementation of this.
Cool, so, thanks.
Yeah, William.
Hi. So this model is interesting because you're integrating forgetting memory into the surprisal framework, which is really cool. The thing that I think is a little bit funny, though, is that you're essentially forgetting the words, right? But yet, I can still remember the word through from your example. But I'm not forgetting the structure, right? I'm forgetting the word. That's weird.
So, so I think the results I presented here, which involved erasures over words, were just because words are a convenient context representation. But that context representation could be a more articulated syntactic structure, and the noise operations could be affecting that structure. And I think that's the right way to do it. So, so the reliance on words and erasures of words is just sort of to get this model started. But the way I hope it goes is richer context representations, and noise applied to those would hopefully give you more sort of interesting structural forgetting effects that don't require word forgetting. So, Colin.
Thanks. I had a question about the structural forgetting findings. And I wanted to wonder ask how you capture what I take to be one of the really interesting findings of the prior studies on this, which is how those are interpreted. So one of the findings, I know Gibson and Thomas showed this, maybe it was shown before, is when people mess up in those cases in English, they take that second verb to have the first noun as its subject, right? And so the way you were talking about it here today, all the action was happening when you get to that final word or not a word.
Yeah.
But an interpretation of that interpretation finding was what went wrong was at the previous step, where that second verb was bound to the wrong guy, and therefore you thought you were done. So, do you have does this model have a way of saying, oh, that's what would have happened earlier, or is that something you would predict would be, that's just how you bail yourself out at a later step?
So the fact that the second verb would attach to the first noun phrase, the model could generate that prediction by, it would have to find a context representation where that's the case, where you take the context representation before the final verb and then apply some noise to it such that you get a representation where the second verb's attached to the first. That could also happen earlier. Whether it happens early or late ends up not actually mattering when you grind through the model. Depending on we should talk about this offline.
Okay.
This is very interesting. So we've worked a lot on modeling the specifics of which verb happens to be deleted, and we're not at the point where we're modeling that it's always the second verb, for example. That is where confusion arises.
Okay, and I'll put in a plug to, we have a poster tomorrow on a Mandarin version of this where there's a missing
saw
noun
that.
effect. So that we're interested to see how this could capture that.
All right, thanks.
Yes, hi. I was wondering if, with respect to the through example, whether what happens, in this situation where you have multiple lexical representations for it. So you have it accompanied by, through up, through away, through out, and then just throw NP prepositional phrase. And the fact that the context doesn't disambiguate actually would predict, and you would be surprised just because you have ambiguity, right? The following the in-between context, so you may not be forgetting or noisy, but rather not helpful.
So you're saying the dependency locality effect there might be because all those additional words have introduced possibilities for ambiguity?
Well,
rather
no,
than
that they
because of this
actually don't disambiguate in terms of the possible versions of throw that is intended.
So in that
So
case,
if you say John threw,
Yeah.
you don't know which kind of through it
Right.
was, and the in-between context doesn't disambiguate. So when you get out, you still have to do that disambiguation.
yes.
So that's not surprisal from their perspective, right? It's just a simple disambiguation. So I'm trying to see whether this, because you didn't talk about multiple, lexical density, right? When you have throw, you are retrieving all of these versions. So how does that get pruned? And how does that connect with with the model?
So we're not currently modeling sort of what happens when you have multiple different interpretations of the context. But in general...
But this is the case in this case.
In general, surprisal theory would actually predict that out would get easier to process because even though that stuff in between doesn't seem to disambiguate, on average, the more stuff you add, on average, it's going to be adding more information. And so out should be getting more easy to process the farther out it gets, the more potentially disambiguating stuff there is in the middle.
But I thought that, but this context doesn't, in terms of, if I remember the context, it doesn't disambiguate it among several possibilities.
This one doesn't, but
throw.
So in that particular case, you don't, but you still get that locality effect in English, even if you have contexts that are not controlled to not disambiguate about the construction, about which particular construction is involved.
Oh, so you did control for multiple subcategorization representations, let's call it, or selection and restrictions on the verb.
So we haven't in this study, but there's previous work on verb particle constructions.
Okay, thank you.
All right. Thanks.
All right. Our next speakers are Frank Malika and Steve Cantadosi, and they're going to tell us about an information theoretic buffer supporting language processing.
Hi. So I want to start off with a puzzle. In psycholinguistics, processing difficulty is reflected in reading times. Now at the same time, people can read 3 times faster than they naturally would under rapid serial visual presentation. So just to give you an idea of what I mean by rapid serial visual presentation, if you stare at the cross, I'm going to show you a sentence presented in this manner. So, right, Jane Austen quotes, right? That's presented at twice your natural reading rate. I don't know if it's exactly precisely controlled on the projector, but it was supposed to be presented faster than your natural reading times. And so now we have a puzzle. If we can process language faster than natural, why do we think reading time rather, is a good index of processing difficulty? And so to investigate this, we've come up with a novel experimental paradigm based on this rapid serial visual presentation. And so our goal in designing this was to understand the relationship between information uptake and information processing. So I just want to lay out some terms first. We have words, and words convey a certain amount of bits, which is information, right? And the relationship between a word and the amount of information it conveys is given by the negative log probability of the word given its context. This is also referred to as surprisal. And so now a listener has to intake this information, right? So some certain number of bits need to be processed just to recognize words. And so we might expect surprisal effects or prediction effects just in this process alone. But then the language user also has to process this word and come up with, their favorite example of a dictator or Donald Trump or kakistocracy. And so let me tell you a little bit more about exactly what we're doing in this paradigm. So we're calling this 5-RSVP. And basically, we present 5 words, each for 147 milliseconds. The first word is immediately masked by the second word. And then at the end of the 5th word, we throw up a mask. It's just uppercase letters, randomized. And that mask stays up until participants are ready to continue to get the next chunk. So now instead of RSVP, where we don't typically get a measure of processing time, here we have a measure of post-presentation processing time. So let me give you an idea of what this one looks like. So again, just stare at the fixation. Right, and so now the participant can take as long as they want before proceeding to the next chunk. Right? I'll spare you the rest of the sentence. And so what we're really interested in is how much does each word surprisal contribute to this post-presentation processing time? And our dependent variable is going to be a regression weight for word surprisal, controlling for a bunch of other factors. So there's a couple different hypotheses about how this could play out. First, we might expect that surprisal does not reflect high-level language processing. It's all about the intake. In which case, we would expect a uniform 0 profile of surprisal weights. So here we have just surprisal weights on the y-axis, and here this is word position. So this would be, it is a truth universally, right, in my example sentences. And so there's 2 different reasons why we might expect this. One, under sort of a perceptual information maintenance account. So if you're just trying to optimally identify a word, right, that's going to be related to how predictable the word is in context. So if it's a really predictable word, you don't need as much perceptual evidence to be sure that you know its identity. Whereas if it's a really unpredictable word, you might need more perceptual evidence before you're confident. And this predictability effect is a surprisal effect. Similarly, you might expect this effect for motor planning reasons or motor control reasons. There's evidence that shows that if a stimulus is more predictable, you're faster to look for it. You're faster to look toward it or fixate on it. And so this is, again, another term of prediction-based surprisal effect that you might expect that has no high-level language processing involved. But now let's say that there is high-level language processing. In which case, there are 2 sort of hypotheses that I want to consider about how language users might compensate. One hypothesis is that language users compensate for RSVP by suspending incremental processing until this perceptual barrage has ended. Right? You focus instead on buffering all of this information, and then you'll process it when you have time to deal with it, because that gets really, really tedious when you're reading, 1,000-word passages in that presentation style. And so under this account, you would predict a uniform profile of surprisal weights, and it would be non-zero, but not crazy big. And so let me show you what actually happens in this sort of, an account, a buffer account. So here we just have the word. So let's say our first word is it. This is just a toy model. That word has some amount of information that it's conveying. So this gets copied into the buffer before processing. If we're suspending incremental processing, then we do nothing during this presentation time. At the end of presentation time, we have the same number of bits. We do this for the next word, right, just copying on. And we do this again for all of the words in our chunk. And now at the end of the day, we have 10 bits of information in our buffer. From each word, all of its information is there, right? So each word's information is going to be contributing to the residual information that you have to process in this post-presentation time. And this is actually consistent with a wide variety of buffering architectures. So you could imagine that information might be processed, the first thing in the buffer is the first thing out of the buffer, or the last thing in the buffer is the last thing out of the buffer. So it would just be first in would start here, move this way, last in would move this way. There's a variety of different frameworks that would predict the same pattern as long as you have a constant rate of processing. Now just to transition, the other hypothesis would be that you buffer and incrementally process as the perceptual presentation is going on. And so in this case, we would expect a linear increasing pattern of surprisal weights as a function of word position. And this is consistent with two different frameworks. It's consistent with the first in, first out buffer, and it's also consistent with parallel processing accounts on average. And so let me show you what this looks like in terms of a buffer model. So here, let's assume that our rate of processing is 1 bit of information every 147 milliseconds. So in this case, we get our word it, we copy it into our buffer, we subtract 1 bit. All right, we get the next word, copy it into the buffer, we subtract 1 bit. Crucially, we subtract the oldest bit in the buffer, right, the first one that was in. And we keep doing this for the remaining words in our chunk. At the end of the day, we have 5 bits of information left in our buffer, and it's basically, wow, that did not work. So there's supposed to be a white bit right there. So shows up right on my thing. But so crucially, you only have truth and universally contributing information there. So there is some information there for processing universally, right? And so the intuition here is that there's information left in the buffer that only comes from the later words that you've seen in this chunk. The earlier words have already been processed, right? And so now this isn't quite the full story. This depends on what your rate of information processing is. So right there, I just used that toy 1 bit per 147 milliseconds. There's actually 3 different predictions that you would get depending on how fast your rate is. So here is your surprisal weight for each of the 5 word positions as a function of rate of information. So at really slow rates of information processing, you end up expecting uniform profile of surprisal weights, and they're all really large. And this is because during presentation, you got like no processing done. So everything is in the buffer at the end of presentation time. Now, on the opposite end of the spectrum, if you have a really, really fast rate of processing, then by the time you get to post-presentation processing window, you've already removed all that information from the buffer. And so you expect this uniform 0 profile. But everywhere in this middle, and this is a really large region of plausible values, you get this linear increasing pattern that I showed before, and I'll show again right here. So just to recap, here are 3 presentations. You have a perceptual motor account where you predict a 0 profile that's uniform, suspend processing where you predict a uniform non-zero pattern, and under an incremental buffer, incremental parsing account, you predict a linear increasing pattern. And now since this is a new presentation condition, this is a new paradigm that we're developing, we included a bunch of control conditions to sort of incrementally make sure that what we're doing is working. So we had a baseline reading condition in which we just gave participants a story and asked them to read it however they wanted. They could scroll up and down just like a web page. And our question here was, are we presenting words faster than natural? Right? We just wanted to get a baseline measure of their reading time. Then we have a word-by-word self-paced reading. Crucially, this is centrally presented, so the participant sees a word like it, that stays up on the screen until they respond. When they respond, the next word immediately comes up, and that stays as long as they want. So it's just your classic self-paced reading, just centrally presented. And our question here is, do we replicate a surprisal effect with central presentation with our stimuli? Right? Just wanted to make sure that that works. Next, we have a masked word-by-word self-paced reading. So the word comes on for 147 milliseconds. It's masked with a random uppercase letter string, and that mask stays on until they respond. When they respond, the next word comes on for 147 milliseconds, and it's immediately masked. And this continues for the entire duration of the story. And the question here is, do we still replicate if we control perceptual timing, right? If we have this precise perceptual timing. So these two conditions sort of directly test our hypothesis that maybe this is all about uptake and not about high-level language processing. And last, we have our 5 RSVP condition, where we're looking to see how language users compensate for rapid serial visual presentation. And so we do an in-lab experiment. The materials, data, and analysis scripts are all online. We have participants read 4 New Yorker articles, truncated to the end at the paragraph containing the 1,000th word. We used a bigram model from Google Ngrams to construct surprisal counts. And each story had 10 complex yes or no questions just to keep people engaged in this task. And so we had 64 participants, 16 per list. And so across list, we just matched story to condition. We randomized the order of which story comes first, which story or condition comes first for each participant, with the exception that the baseline comes first so we can actually get that baseline reading time measure. Cool. And so not to keep you in suspense, just participants succeed at this task. So here's accuracy as a function of presentation condition. And so it's above chance for all of our presentation conditions, suggesting that people can do this sort of reading and comprehension at this fast presentation rate. And the other sort of manipulation check we have in place, we just wanted to make sure that participants all read, our presentation time was all faster than participants' natural reading rate. And that holds true for all but 3 of our participants, but it turns out if you include them or exclude them from our analysis, it doesn't change anything. So we keep them in. So now returning to our hypothesis that surprisal does not reflect high-level language processing, right? I said this was tested by our self-paced reading condition, and specifically this is tested because there's no eye movements involved in central presentation. So if there was a motor planning account, we wouldn't predict surprisal effects. Similarly, in the mass self-paced reading condition, we're controlling perceptual information. So if surprisal is all about perceptual optimal information gain, then we wouldn't expect to see a surprisal effect here. So not to keep you in suspense, here is the surprisal weights for our self-paced reading and our mass self-paced reading conditions. They're both significantly greater than 0, so we have surprisal effects. And these surprisal effects suggest that it's not the case that surprisal is all perceptual motor planning, right? There's probably some high-level linguistic processing, although I'm foreshadowing. So going back, here are the predictions for our 5 RSVP condition. Given what we've just seen in those previous 2 conditions on the word-by-word self-paced reading and the mass self-paced reading, this is sort of unlikely. It's the weakest link. So we're really going to be considering suspend parsing, in which case we get a uniform pattern, or incrementally parse, in which case we predict this linear increasing pattern. And so to show you the data, it sort of suggests that there's a linear increasing pattern. It's actually significantly different than a uniform pattern. And now what's really cool about our first in, first out buffer model is that we can now take the data and fit our model predictions to infer what their best rate of processing is. And so if we do this, we get model predictions in red, which provide a good match for our data. And we infer a rate of processing of 18 bits per 147 milliseconds. That's 123 bits per second. And so just a note about rates. First, that estimated rate is reasonable for RSVP. I know that it might seem fast. And let me provide sort of a back-of-the-envelope estimation to give you an idea of why this is okay. The average word in our materials, at least, conveys approximately 10 bits. So at 123 bits per second, that's approximately 12 words per second. And that meshes well with the RSVP literature, suggesting that 12 words per second is the maximum speed at which humans can still do the task and retain what they're reading. Now that being said, we should take our estimated rate with a grain of salt. So if you have flexible or adaptive systems, or if you think that language use is flexible and adaptive, then you could suggest that you might offer different resources. You might allocate your resources differently in rapid serial visual presentation conditions. This task is not natural reading. It's actually a lot more cognitively taxing. And so if you have that ability to sort of meta-reason, you might reallocate your resources and pay more attention to processing in an RSVP situation than in a natural reading task. Okay, last point, and this is the most important point, is that 5-RSVP is a method for estimating these processing rates. So while I'm saying don't take our rate with a grain of salt, this is a cool tool to now study processing rates. And this has important implications for sort of psycholinguistic studies. First, an incremental first-in, first-out buffer is a formal model of spillover effects. So you could imagine that we finally have an answer now to our age-old question that we stay up nights worrying about. When does my spillover region end, right? And so just to qualify what a spillover region is, in a sentence such as the experienced soldiers warned about the dangers conducted in the midnight raid, we predict processing difficulty at conducted, right? But normally we observe the effective processing difficulty, which we measure as increased reading times, on the words that follow, like the midnight raid. And so that's what a spillover effect is. And so you could imagine that you could use this incremental first-in, first-out buffer to independently fit what the rate of information processing is for your subjects, and then predict where you should see these complexity effects, where you should see this spillover. Cool. So now, I didn't really talk much about this before, but we're consistent with the first-in, first-out buffer. We're also consistent with the parallel processing account. So just to remind you, first-in, first-out buffer, again, that did not come through. There's white there. So in our first-in, first-out buffer, we have the last two words are contributing at the very end of the day, right? And so now I'm just going to show you what one sort of formalization of a parallel processing account. There are many. So in one situation, you can imagine that for every word, for every unique word you have in the buffer, you can just remove one bit. So in this case, the first word goes into the buffer, you remove one bit. The second word comes in, you have 2 bits in the buffer, you have lots of bits in the buffer from 2 words. Bits in the buffer from 2 words, and you remove 2 bits, 1 for each word, and you continue doing this for all of the words in your chunk. At the end of the day, you still have, there's supposed to be 1 white bit there, you still have bits of information from just the very end of the 5-word chunk, which suggests that the earlier words are already processed, and again, the later words are what's contributing to this post-presentation processing time. So it's the same intuition. Like I said, there are many other ways that a parallel processing model might work. So just summarize and give you the take-home messages. 1, there are high-level language processing related surprisal effects in RSVP. 2, language users compensate for RSVP using an incremental linguistic information buffer. And 5-RSVP, that new presentation condition, is a way to control perceptual and motor effects on reading time. And this allows us to use reading time as an index of processing difficulty, where we don't have to worry about the perceptual or motor effects. And it also allows us to estimate the rate of information processing, which can then be used as a formal model of spillover effects. And so I just want to thank Steve, Jenna, the Koala Lab, Roger Levy, Tim O'Donnell, Mike Tannenhouse for conversations, Center for Language Science at the University of Rochester, the CUNY organizers for organizing everything, and thank you all for listening.
Hi, I'm Roger Levy. Thank you. This is really interesting. I like it. I have a couple of questions. A couple of technical questions just for clarification, and a high-level question. So the technical question is that maybe if you could just say a little bit more about, I think I know the answer, but like the, how did you estimate the surprisals?
How do we estimate the surprisals?
Yeah.
Google Ngram's bigram model.
Oh, just a bigram model?
Yeah, just a bigram model.
Does that work better than higher order models?
Haven't tried that yet.
Oh, okay, great.
It's on the agenda.
Okay, cool. My other question is just about, I want to know more about the, could you say a little bit more about the way you're deriving the predictions for the surprisal weights? It seems intuitively like for a first in, first out incremental buffer, that the predictions about weights, according to the schematic that you laid out, depend not only like on, I mean, it's going to depend on the distribution of surprisals of words above and beyond just the sort of average number of amount of surprisals. Just to give a sense of this, if the average word, could you bring up the slide where you sort of show the multiple curves? You have the sort of
that guy, yeah.
those curves. Yeah, that slide. Yeah, great, thanks. So let's say that like the average word actually falls slightly below your information processing rate of that 25-bit cutoff, but there's very high variance in the actual surprisal value of an individual word. So actually maybe about 30% of them fall actually above that information processing rate, and that's going to give you some, it seems like that would actually pull those lines apart a little bit. So
Yeah.
I'd like to hear a little bit more about your assumptions about how you did this, especially given that you fitted a model like this to the data.
Yeah, so these are predictions based on the materials, the surprisal values that we used in our actual materials. But you're right, the predictions here might actually move depending on the variance of the actual surprisals in the materials that you use.
Great, thanks.
No problem.
I'm Ev Fedorenko. The optimal, the actual information rate was like 123
Bits per second, yeah.
So we talk considerably slower than that, don't we? So or how close are we to that in actual communication? And if we're slower than that, is it just kind of low-level motor articulatory constraints or something else?
So that I don't know enough to properly answer.
But we do
honestly.
talk slower than that, yeah.
I think we do.
Yeah.
In terms
Most
of
times.
yes.
Quick follow-up question based on that. That 123 is based on your bigram model, right?
Yeah, it's based on the
So it's
bigram model.
actually, since that's an overestimate of the surprisal rate, right? Because the bigram
Yes.
model is actually going to be an overestimate. Really, when you take that into account, it's going to be a lower number than 123, right?
Probably.
Great, thanks.
So I was thinking about how your results might have impacts on a context in which RZP is used really often, which is EEG studies and fMRI studies. And I was thinking about if you had any thoughts about kind of like rate of representation for those kinds of studies and ways in which that might impact kind of incremental processing in like EEGs and how waveforms might be shifted.
So that I'm not really sure. I don't know what the average presentation rate is that are used in these experiments. But if the RSVP presentation rate allows you to process and it isn't like too fast, then I could see that it might not have an effect. But I honestly don't know. I'm sort of speculating wildly.
Hi, Jerry Altman at UConn, as distinct from the other Jerry Altman somewhere else. So I just wanted to ask about the grain of salt with which we should take the rate of my word production. And following on from something that came up talking to Roger, of course, the individual words will have their own individual information that they're conveying. So different words, different bits, and so that means that for an individual sentence, in fact, you might imagine that you want to change the rate for individual words in order to optimize the presentation. Now, because you're giving the same rate for each word, that means that the estimate you're getting of the optimal rate, if you like, or the slope, I don't know how does that actually, is that an overestimate or an underestimate? It's going to change my sentence. I'm just not sure how we use that information.
So that rate would be for all of it overall, like averaged over sort of all of the trials, all of the chunks that people see for individual stories. It is sort of an overestimate in terms of the fact that we were using a bigram model, and so you would expect it to shrink a little bit, as I just said to Roger just brought up. But I don't, like we could manipulate the presentation rate or the distribution of surprisal among the word positions to specifically get like different effects, sort of like second words contributing more and like fifth words not contributing at all. And that's actually a really strong prediction of some parallel accounts. But I'm not quite sure exactly like how you would want to optimally, if you're trying to just optimally present the sentence, then yes, you would want to customize the presentation times for each word.
I guess the question I'm asking is, imagine you have a sentence that's just full of very high-frequency words with very predictable bigrams versus a sentence that has very low-frequency words with very unpredictable bigrams. The rates you might get from a method like this would be very different.
Oh, yeah.
And so I'm getting some picture, if you've sampled enough sentences with enough words, I'm getting some picture of something in bits per second. I just don't know what that something really is reflecting in the language. In that is, what kind of information is it, about words? Is it about syntax as well? Does it include semantics? I'm not really sure what to do with that number in a theory, that's all.
Oh, theoretically, I'm not sure. It depends on which theory of sort of processing you want to play with. Here, I'm just talking in generic information processing terms. Just if you have a solid amount of information and you want to process it incrementally.
Hi, I'm Peter Gorton, as distinct from Jerry Altman, mercifully. So I was wondering about the RSVP rate of 12 words a second, and I know that estimate, or even perhaps faster estimates, are in the literature from, I think, Ken Forster's work, but my sense was that there was a real limit to the length of a sentence that you could process at that rate. So is my recollection correct? And then also, what was the length of the sentences you looked at?
So first, you're correct that in one way, they have to have a post-processing break after each sentence in order to be able to go at that rate. So normally they give, after a sentence, they have a 1-second break before they continue to the next sentence. In our task, it was always 5-word chunks, right? So in that regards, I don't know exactly how long our sentences were, but we kept constant what the RSVP chunk the participant was getting was.
So it was the RSVP rate for sentences broken up into 5 words, and then there was a pause.
Oh, for us, it was just 5-word chunk, and then you get a mask, and that mask stays on as long as the participant wants it to. And then they click to advance to the next 5-word chunk.
Okay. Thank you.
Thank our speaker.
Ja, ich mache schon mal.
So yeah, so this should plug into you, and then you're going to have this on the other side, which is our HDMI, which is actually what we're trying to get everybody to use.
That's great. That's great. Because
Yeah.
I was thinking of the blue.
The VGA.
The
okay,
VGA.
yeah. So,
That's not
so yeah, this is what
We
you
don't need
want, and also there's going to be a few of these here also.
Also,
just plug in during one of the breaks and try it out.
Yes,
Totally welcome to.
yeah,
Yes.
because there's also these mirror displays that Richard F. were
Yeah,
dealing with yesterday.
yeah.
To get to that screen, so if nobody can see what I can see, I'm
Definitely try it, and when you're trying it, if you want to come grab me and I can help you.
Well, I love to test, yeah. And I want to show, That's how I just
That's mine, yeah.
I mean, they don't have
So they only seem to have HDMI. I don't know. I need VGA, so I don't know how we're going to do that. Maybe there's
That's annoying, yeah.
What sort of connector would you need? Yeah. So there's a bunch of adapters here. Don't know if those will work for you. Should we ask? We need to ask someone. What did he say? They're coming up. You've moved. It's booted into Linux. So what's your? I could probably boot into Windows. What's your presentation? Yeah. So let me try to get the connector sorted, because at the moment I can't even connect this laptop to the projector. So. Yeah. So maybe we're missing something here. This is what power supply. This is temperature.
This is a Mac that anyone can use for.
Great.
But you know, that's oh, that's okay. Yeah. Oh, hold on. Yeah. This is to be used. Hey. Are you later? Okay. Who's after me? You're after me.
Yes.
And what was your problem?
Well, I was wondering if I need to use my colleagues.
No, you can use this.
Yeah, because turns out for mine they have to switch to the input, and it's a bit more complicated.
So let's take your.
Let's review my. Well, I might come back. If this works, it's fine.
Here you go. Where's?
It's Michael who's presenting. I don't know where he went. Okay, great.
Okay, do I need any?
Yeah, I didn't manage to. Yeah. Oh well. Let's try this.
Hello.
Hang on a second. Let me, hang on a second. Let me see if I can make this work. Let's try the.
Okay, okay.
Well, I'm hoping to use
There,
one.
yeah, a bunch of people are loading.
Okay.
Oh, so do I need to know the password?
We can write it down. Yes.
Before my
Do you have a pen or something? To write it, just to like.
All right. Okay. Great. I probably need to log out. Sorry, I'm just getting this.
Probably. But if not, I'll come in.
Keynote?
Sorry?
You ran Keynote?
No, PowerPoint, but that's, I'm just, all I did is double click it.
Yeah, he's trying to get you to run Keynote. When I opened it in
Sorry. Take
Yeah,
a
I'm still
second.
gonna, I'll try PowerPoint, and if not, I'll use the PDF, but let's see first if I can do PowerPoint.
Shit.
So yeah, how do I even, why is it not?
Assuming that everybody knows all the rules.
Hey, you gonna use this thing?
Just do like family presentation. Yeah, but this, you get to get
Oh,
started.
some screen mirroring is going on. Just a problem with the screen mirroring.
Okay, so let's first see.
Yeah.
Okay, now, I need to use a PDF. I can already see it's not good. So where do I, turn it off and not push it off?
Can I give you an email address to mail your slides to the captioners need it?
Okay, yes, I can.
Yep. Review. Yeah. No, I timed it last time.
We were on the right track with WordNet and then and I can see that it's in also.
Okay. Fine.
But it doesn't.
Hi.
I don't know if that's the password.
So what exactly is the problem?
They can't download it, so we can just
Okay.
email it to them directly. Because the best choice, they look at your slides so that they can spell the
Yeah,
words
okay.
correctly,
Seems to work.
and everything like that. So they really need to have the slides so that they can be looking at them.
I'll just
Do you need it
here.
right
Oh,
now?
but I didn't check the
Yes, so right now.
How do I?
Yeah. If you want to try that, if you want to put this in we just need the HDMI. That'll probably work, but we should try it.
I'm gonna plug you for a second. Is that okay?
Sure, yeah.
Reporting and that's
And I can probably.
services.
What happened here?
How do I?
I don't know. Could you just give?
Yeah, let's do that.
Why don't you copy it to me as well?
Okay. Your email?
MEKLI.
Hey, Idan? It's like, oh, there it goes.
So what happens if I put it in? What do I do?
I have no idea.
Okay, I want to just escape so I can also, like, it's already here, I can take off my stick, so then it'll be.
Yeah.
How do I, where is it over here? Sorry, I don't have a map. Where do I go to,
Pull that out, you can just pull it
I
out.
cannot do that safely, whatever.
Well, it'll be fine. It's okay. I don't know why it just went dead. Blank screen. Yeah. Any idea why
I'm
that
gonna
would be?
put this up on the screen. Is that okay?
So what are the email addresses?
I can enter them.
Unless it has some.
Okay, it's automatically there, I don't need to do anything
Okay.
on the screen.
It might be
Thank
a
you.
thing where like it thinks it's
it thinks it should send the signal to the other screen.
Just to see that it can be.
Good?
Yeah, it works.
Okay.
Okay. So I'll just, well, I guess
Okay,
we'll.
yeah, that one he has to go to the first one.
Back on the screen, is that okay?
Yeah, it's fine.
Second
Trying
slide.
to help if something doesn't. Can you
Okay.
pretend that
Well,
we
you'll
understand
see
how to
first.
help?
Yeah, especially if again gonna just be blank, like, you know, just black like beforehand. And, yeah. Okay.
Of course you do.
Okay.
Okay, das ist schön.
Okay, und hier einfach vorwärts, rückwärts. Vorwärts. Und du siehst hier ja auch, und zum Zeigen, das rote ist ja der Laserpointer. Aber
Und das ist das Mikro.
das ist das Mikro, und du musst scheinbar hier relativ direkt davor bleiben, damit die Dolmetscherin dich sehen kann und weil die es natürlich auch aufzeichnen. Ja.
Okay, gut.
Und ich würde so wenig wie möglich pointen, weil es ziemlich unnatürlich ist. Aber ja, wir haben ja gesagt, das Critical Role und so Sachen. Ne?
Genau.
Also ja, viel Glück.
Schön, ja, gut.
Wie viel Zeit haben wir denn noch?
1 Minute, theoretisch. Aber die Leute müssen alle noch kommen.
52.
Ach so, ich habe 54.
Okay.
Die Leute müssen auch kommen, also insofern.
Ich schau mal, ob Melissa die Folien gekriegt hat.
Ich habe vielleicht den Namen falsch geschrieben.
Bitte?
Ich war mir bei der E-Mail-Aktion nicht ganz sicher, das war falsch.
Ja, ja, aber sie war ja dann noch im CC. Ja,
Genau.
von daher müsste es sein.
Sorry, would you guys mind if I just tested this out really quickly?
Okay.
Yeah. Perfect. Okay. Thank you.
Should I?
Yeah, if you don't
Should I
mind.
unplug this one or this one?
I think this one is our special.
Well, actually, I don't know if you need to unplug anything. I need a VGA port.
Yeah, so we don't have VGA.
Oh, but then they have these dongles though.
Okay, so that's problematic because this has got USB-C ports. There's no VGA cable here. That's not going to work. This only has.
This? Oh no,
No,
that's
it
all the
needs to be-
same.
yeah. I can transfer it over to. Is there a conference computer? I don't have a stick.
I have a stick.
But it's USB-C still.
Oh my
The
god.
joys of having a new Apple computer. Can I email it to someone who has? Can I email it to this computer? No.
So no one has a newer Mac, huh? You are so fancy. Cheers.
We just need that to plug in to this thing here. What's that? Are you talking to me or? Oh, I don't know.
I'm so glad we came here.
I'm not sure.
This happened at LSA. They didn't. They all had this type. No one else.
Yeah, I mean, I just need like one of these, and then I can plug it into the VGA. And then it sounds like that's what other people are doing, right? So that should be
It's only an issue if you have like the newest one.
No, it's a couple years old.
Yeah, yeah, yeah.
Can we use these as speakers or are they for?
Yeah.
Oh, awesome. Ja, wahrscheinlich.
So, can we try to get you going HDMI?
This only has USB-C ports.
Okay,
and an
I have
adapter.
I have a.
HDMI to. Oh, okay, perfect. Yeah. Yeah. Thank you.
Oh no, didn't grab a spoon.
Oh, awesome.
Are you first?
No, I'm just testing it out. I'm third or fourth.
Is the audio coming from that?
No. Perfect. Okay. Thank you so much. And that'll just be here? Okay. Thank you so much.
I'm up in the booth. Goggles here for everybody. Maybe we should use. Yeah, that's good. I'm glad we have
Ach so, ja, gut. Fast nicht genau. Ja, kann man nichts machen.
Nee, das ist das Standard-Beamer-Format. Das ist halt nicht so breit. Ja. Ich müsste mal einen Beamer ändern, den man komplettieren.
Ja, gut. Das hätte ich drin.
Okay,
ja.
That over. Should I wait for people to trickle in?
I'd wait until.
Okay. Do that. Sorry to send you on a goose
Sure.
Okay, welcome back. Okay, welcome back. We're starting a little bit late. Okay, welcome to the next session. The first paper that we have in this session is Modeling Task Effects in Human Reading with Neural Attention by Michael Hahn and Frank Keller, and Michael Hahn is presenting.
Thank you. Is this okay? So this is joint work with Frank Keller on human reading. So this talk will have two parts. The first one on a novel neural reading model, and the second part on how it explains task effects in reading. So here is an extract from the Dundee eye tracking corpus. So we see that a reader's eye movements move forward in discrete fixations where the eye is static, and saccades where the eye moves very fast from fixation to fixation. We see that fixation times vary from, in some cases, about 100 milliseconds, other cases 300 milliseconds. And crucially, we see that many words do not have a fixation at all. So all these blue words have no fixation. And actually, in the Dundee corpus, about 40% of all words are totally skipped by the reader, which is interesting because people understand text without problem nonetheless. Now, there have been a range of computational models of these phenomena. So there are models of saccade generation, cognitive psychology, like prominent ones including Easy Reader and Swift. There are also machine learning models that are trained on eye tracking data. Now, these kinds of models require the selection of relevant eye movement features and then estimate parameters in a supervised fashion from an eye tracking corpus. There's also the approach of using Bayesian inference. So here the idea is to maximize speed of reading while reliably identifying the text. This is an idea that we're also going to take up in our approach, and it is known to replicate effects of things like predictability and frequency on eye movements. However, this approach so far has only been evaluated in a very small corpus, and it also assumes the fixed task of word identification. Another crucial approach is surprisal, which, as we've heard in previous talks today, measures the unpredictability of a word in the context, so the negative log probability of the word in the context. This is known, as we've heard before, to predict word-by-word reading times, but since it's designed as a model of processing effort, it cannot explain things like regressions, refixations, spillover, and skipping. So we've seen that 40% of words are skipped, but it's not clear from the surprisal point of view why that exactly would be the case. Our goal in this work is to build an unsupervised model that accounts for reading times and skipping in a wide coverage fashion. And our basic hypothesis is that there is this trade-off in human reading between precision of language understanding, performing some language-related task as well as possible, and on the other hand, to fixate as few words as possible in this process. So there's this trade-off of two conflicting goals that is optimized in some way by human reading. Our assumption is, so there's this task that's been performed by the reader, but we don't fix the task yet. So it could be any task, and different tasks might yield different reading behaviors. So for now, we assume that the default task is to reconstruct the text, including the skipped words. And our approach, which we call neural attention trade-off, or NEAT, is as follows. We develop a generic neural reading architecture that integrates neural language modeling and a neural attention mechanism. Then we train this end-to-end to optimize for this trade-off between precision and economy, and then evaluate on an existing human eye tracking corpus. So the architecture is as follows. We assume we have an input sentence consisting of, in this case, just 3 words, W1 through W3, and we have this reader that consumes these words one by one. However, it doesn't always consume the word, so it has an intermediate attention module A, which decides for each word whether to show the word to the reader or whether to skip the word. So in each time step, the reader makes a prediction about the next word. This is this P, and then there's the attention module, which makes a decision about fixation or skipping. So assume it decides to fixate the first word, so the first word is shown to the reader. And the second word might be skipped, and in this case, the reader receives a dedicated skip representation that says nothing about the word, just that a word was there and it was skipped. The same computation is done throughout the whole text. And after the end of reading, there's a decoder module that tries to, based on the representation of the reader, reconstruct the full text, crucially including those words that were skipped and so aren't actually accessible to the reader. Now, all these modules, reader, attention, and decoder, are implemented as general-purpose neural networks. So to implement the trade-off hypothesis, we define a training objective. So we want to solve prediction and reconstruction with minimal attention. So we have this sum, weighted sum, of, on the one hand, the loss that is incurred by some reading strategy on prediction and reconstruction. And on the other hand, for this reading strategy, we have an expected number of fixated words. So both of these things should be low. So the first one encodes accuracy on the task of reconstruction, and the second term measures the economy or lack of economy. So we train these neural network components end-to-end using standard gradient-based optimization for this objective. And crucially, we do so in a totally unsupervised fashion, so there is no grammar or lexicon or eye tracking data. We just take a large chunk of unlabeled text and train the architecture that I've shown to you for this objective. For the evaluation, we go to the Dundee corpus, which consists of 20 texts from the independent with eye movement data from 10 readers. This consists of about 360,000 words, where about 60% of the words are fixated and 40% are skipped. So in the results, we see that NEAT can predict human fixations with an accuracy of 63.7%, which is above a random baseline, but there's room upwards to a supervised model. We see that surprisal derived from NEAT can predict reading times, even though it only looks at 60% of the context words. And we can see that NEAT predicts the effects of frequency, length, and predictability on fixations. We've seen that the correlations between successive fixations are predicted, and reading times across part-of-speech categories are predicted. So here we see fixation rates by part-of-speech category. So the red ones are the actual human data from the Dundee corpus, and the blue bars are the NEAT predictions. And we see that for most categories, there's a relatively good fit. So for adjectives, nouns, verbs, we have high rates, and for things like determiners, conjunctions, there are low fixation rates. And note that crucially, we do not tell NEAT anything about POS, about part-of-speech tags or anything like that. It has to infer this from raw text and the unsupervised training objective of having this trade-off between precision and economy. So we've seen that that fixation rate across POS categories are predicted. Now let's look at a real text. So this is an extract from the Dundee corpus with human fixation probabilities as estimated from the 10 readers. So blue words were fixated by no one, red words were fixated by everyone, and there's this gradient in between, and white words are missing data for various reasons. We can compare that to predictions made by NEAT, and we see that in both cases, short words, function words, frequent words have very low fixation probabilities, long words, content words, rare words have high fixation probabilities. Now we've seen that this trade-off hypothesis, when used as an objective for an unsupervised neural network model, can replicate various known properties of human reading. So let's get back to our initial trade-off hypothesis. So we stated that there is a trade-off between a task, performance, and economy, and we assumed that the task was to memorize the text. However, if we change the task, then the precision economy trade-off will probably change, and we should observe different kinds of reading behavior. And indeed, there's independent prior evidence that changing the task in reading changes the reading strategy that humans adopt. We tested this with a question answering experiment. So we had two conditions, a no preview condition and a preview condition. So in the no preview condition, participants read a text and then saw a question and answered it based on the text. In the preview condition, participants first saw the question, then read a text, and then answered the question based on the text they read. So we had 20 texts from newspapers, and with one multiple choice question per text, 10 participants in each condition. texts and questions are taken from a large-scale question answering corpus, and we use an iLink 2000 tracker. So here's an example for the preview condition. People will initially see the sentence with a blank, then they see a text, and then they see the same sentence with a blank and 4 possible answers. In this case, the right answer would be machine. So this was the preview condition. Crucially, in the no preview condition, this preview of the question would be absent. Now, looking at the reading behavior, we can observe that in the 2 conditions, the fixation rates are quite low. So in the no preview condition, people only look at half the words, and in the preview condition, they actually skip 2/3 of all the words that are in the text. Similarly, for first pass durations, we get a difference of about 50 milliseconds in average between the 2 conditions. Nonetheless, people do quite well on the task of answering the question, and they do even better in the preview condition, even though they only looked at 1/3 of all the words. Now, looking at more detail with mixed effects models, we predict first pass durations and total times for each word. So we get a few main effects. So we get that people are slower in the no preview condition, which we already saw, that people get a bit faster over time in the text, they slow down for named entities, and there's an effect of surprisal. And there are also these interactions with the task, and I'll go through them one by one. So here we see the total times plotted over the surprisal. So the top line is for the no preview condition, the bottom one for the preview condition. We see that in both conditions there's an effect of surprisal, but the magnitude of the effect is very different. So the effect is much larger in the no preview condition. Now looking at first pass durations over precision in text, we see that in the no preview condition, people get a little faster over time. In the preview condition, people actually slow down in the middle of the text on average, which turns out to be because the actual correct answer tends to be in the middle of our texts. Now looking at the actual correct answer where it occurs in the text, we see that people slow down a lot. So they slow down from 250 milliseconds to 500 milliseconds for tokens that occur in the correct answer in the preview condition, but not in the no preview condition, where they presumably cannot infer what the correct answer was. So we have seen that NEAT predicts that there should be task effects in reading, and we've seen in this question answering experiment that there actually are these kinds of massive task effects in this task variation. Now we want to model that in NEAT, so we again have a text, so W1 to W3 is the text, and then there's this question, Q1 through Q3. As before, we have a reader that advances through the text, and the attention module decides whether to read or skip a word. Now, crucially, in the preview condition, the reading behavior is conditioned on the question, which means that the attention module should also have access to the question. There's a link in the neural network architecture from the question to the attention module. As before, we have this computation of either fixating or skipping. So in the end, we build a representation that includes only the fixated words. This is then given to an answer selection task module. So this looks at the representation of the reader, crucially only including the fixated words, and a representation of the question, and uses this to select the answer it thinks is most likely to be the correct answer to the question given the text. Crucially, in the no preview condition, we simply cut the links going from the question to the attention module, which means attention, the reading, will be independent of the question. So this is preview and this is no preview. Now we need a new training objective, as again we want to have this trade-off between precision and economy. So for precision we have the loss on question answering, which encodes how much probability mass is wasted on incorrect answers. And we have for the economy the fixation rate. Both of these things should be low. So we train the neural network components on this objective, and we do so separately for preview and for no preview condition. So we get 2 models, one for each condition. We use the same large-scale question answering corpus for training that we used for the human eye tracking experiments. And as before, the training of the neural network components only includes the corpus and this objective. There's nothing else that influences the predictions. Now we want to test whether the attention variable, the fixation rates that NEAT predicts in this task-based model, can improve prediction of human eye tracking data over surprisal. So here we have a mixed effect model for first pass times. We have various baseline predictors, including crucially surprisal. And we see that a residualized NEAT attention, the residualized NEAT fixation probability, improves prediction of human first pass durations over surprisal. Similarly, for fixations and skippings, we can see that human fixations are predicted, prediction is improved when we include the NEAT attention variable, which crucially also accounts for the task in contrast to surprisal. Now, qualitatively, we can again go to heat maps. So here we see human fixation probabilities of one text from the corpus in the no preview condition. We see fixations are spread over the whole texts. Long words are basically fixated no matter where they occur. In the preview condition, there are much fewer fixations, and they are concentrated towards certain areas, presumably those areas where the reader suspects the correct answer to be. For the model, in the no preview condition, we again see fixations spread over the whole text, and we see lots of very high fixation probabilities. In the preview condition, fixation probabilities are lower, and they are again concentrated towards certain areas of the text. So to conclude, I presented NEAT, an unsupervised neural network model of reading that is based on the trade-off between precision of understanding and economy of attention. We've evaluated on the Dundee corpus for normal reading, where we've seen that it predicts human skipping behavior and that various known qualitative properties of skipping emerge, like differential skipping rates across POS tags. Then we've seen that NEAT predicts task effects in reading. We've tested this in a question-answering eye-tracking experiment, where we've seen that preview interacts with text precision, named entities, and surprisal. And we've seen that NEAT can capture these task effects using a model that performs question answering. Thank you.
Okay, we've got a little bit of time for questions. Please state your name before you state your question. Ask your question.
Should I? Tava Linzen. So very nice work. My question is about the similarity to humans of your question answering model, where humans are usually not trained specifically on a task of answering questions about a task with millions and millions of words. We're more flexible in the way that we adapt our task to a reading strategy to the task. So I was wondering if you had any thoughts about how you can make the model adapt more quickly to a new task, or yeah.
Yeah, that's a very important question. So I think the answer to that is that humans already have this experience with various tasks that they know how to solve, and they know how to adapt to different tasks, while the neural network model doesn't have, in current technology approaches, doesn't know how to adapt to new tasks. So I think there's this larger question of how machine learning models can adapt to new tasks, and I think that's for now open. But it would be very nice to have something like this in the future.
Hi, Scott Frondorf, University of Pittsburgh. So you started off by saying that one of your assumptions is that sort of the default task in reading is to memorize the text as completely as possible. And so I wanted to sort of ask about the sense in which you meant that to memorize it as like in as much detail as possible, because it seems like the behavioral finding is often that people don't have very good memory for a lot of the details of the text. For instance, they don't remember whether optional function words were included or not. People have very poor memory for that. What they remember is the meaning. They don't remember all of the surface level detail of what optional function words are included, or even the exact words that were used, or the word order. And so could you expound on maybe what you mean by saying that the default assumption of the text, the default assumption is that people are trying to memorize the text as much detail as possible?
So I guess one answer is that this is essentially, oh, this is too slow. This is essentially replicating the idea of the previous Bayesian models, where the idea was to identify the text. And here we want to also identify the text after finishing reading it. So in both approaches, the idea is to identify the text word by word, which is probably just an approximation to actual understanding, which should include something more semantic.
I mean, there are cases where you're trying to memorize things word for word, like you need to memorize Hamlet's soliloquy or something, and then it seems like that's a very different task to just sort of natural reading.
Yeah, it's possible that it would, so there should be task effects that we observe between this and a more natural objective for normal reading, yeah.
Thank you.
Liz Schotter, University of South Florida. So I was wondering, in your task comparison where you give them a particular question to answer, they're probably going to just be skimming the text and looking for the one part of the text that answers that question. So it's unsurprising that they're going to be skipping a lot of the words. Have you looked at regressions back to the word that would answer the question? Because presumably when they're reading normally, they don't know that that's really important and really informative. So they would be less likely to skip it initially, but maybe wouldn't be very likely to go back and look at it again. Whereas they might be more likely to skip that particular word initially, but then realize that this is the sentence that's really going to help me answer that question in particular. And they might be likely to go back and actually, try and figure out what the particular answer to it is. So have you looked at regression behavior or rereading, particularly in that area of the text?
So we didn't evaluate it statistically, but impressionistically that's the case as you described it.
Okay, yeah, that'd be interesting to look at.
Yeah, that's right. Yeah, we'll try that.
Thank you.
Okay, we've got a little bit of time for additional questions, if there are. Well, I've got a question. Have you thought a little bit about using neural networks for doing things that we might like to have non-opaque models for? So neural networks are a bit hard to interpret.
So one approach for that would be to have certain predictors that we think are important and add that to the neural network as additional information, and then see what the neural network figures out about these. And the neural network could still figure out additional things that we didn't think of. So the neural network figured out all these POS and frequency and so effects, even though we didn't tell them it about. So a cool thing with neural networks is that they can figure out things that we didn't think about, and if they can figure them out. And it might be hard to get that in an interpretable model that only has features that we put in the beginning.
So you can take some of the features and remove them, sort of ablate them out, see if the network can still do that, and then those features will be important contributors? That's one way of...
That's one way, yeah. Or we can have, it could learn coefficients for these predictors, and then we can see whether they become positive or negative or zero, or something like that.
Have you started any of that yet?
Yeah, I started working with that, but there are no results yet.
Jonathan Bellinkov. It seems, if I understand correctly, that you're doing a hard decision of whether to skip a word or not. In neural attention models, there's often a soft attention over, say, words. Have you considered doing a soft decision of whether to skip or not? And if this is supported by evidence on human language processing at all?
Right, so in the neural network lecture, there is this hard and soft attention, as you point out. And so we've used a hard attention approach since human reading is discrete. So there are discrete fixations, and a word is either fixated or not. So human fixations are not gradual the way that soft neural attention would be. So that's why we chose a hard attention approach.
Okay, are there any more questions? Well, if not, let's thank our speaker. So our next presentation is titled People with Smaller Social Networks Are More Influenced by New Speakers. And the speaker of this presentation is Shiri Lev-Ari.
Oh. Oh, this looks a bit strange. Okay, so hi everyone. So as was said, what I'm going to try to show you is that people that have smaller social networks are more influenced by each speaker that they meet. But before I do that, I want to explain what I mean when I use the term social networks. So when I use the term, I'm not referring to social networking websites such as Facebook. I'm also not referring to the friends people have. So for me, social networks is just the people that someone regularly interacts with. Now, they might be his friends or his family, but they might be his students, boss, clients, just anyone we regularly interact with. Now, to give you an intuition why it might be the case that people with smaller social networks might be more susceptible to the influences of each speaker, pretend that you only know 2 colleagues who attend this conference, and one of them always calls it the CUNY conference, and the other person always calls it the sentence processing conference. Then you might conclude that CUNY conference and sentence processing conference are equally common labels for this conference in the world. Now, if you meet a third person, and the third person also says CUNY conference, then you would have to adjust your representation, and you're going to conclude that actually it seems that CUNY conference is twice as common as sentence processing conference as a label. Now, let's say that instead of only know 2 colleagues who attend this conference, you know all these people who attend this conference, but again, half of them regularly call it the CUNY conference, half of them regularly call it the sentence processing conference. So again, you should assume that they're equally probable. Of course, again, you might meet someone new, and that someone new might call it CUNY conference, so you would have to adjust your representations. But of course, this time the adjustment is going to be much, much smaller. And the point is that there's an inverse relationship between how many sources we have and how much weight we give each and every source. Now, you might at this point pause and wonder, why am I talking about number of sources, and how do we know that we even pay attention to that? Isn't it just raw frequency? Well, I'll just start with the intuition that we would be pretty bad statistical learners if we go back to the first case, we're going to conclude that sentence processing conference is 3 times as common just because the colleague that we know that uses that term talks 3 times as much, right? But we don't have to really rely only on our intuition. There's actually evidence that show that already children and even chimpanzees actually pay attention not just to the frequency of a behavior, but to the number of individuals that actually display that behavior. So for example, in this really nice study, both 2-year-olds and chimpanzees basically saw 6 demonstrations of individuals with conspecifics drop balls into these colored boxes, and every time they dropped a ball, there was an apparatus that opened up and they could take a treat. Importantly, in 3 different demonstrations, there are 3 different individuals all the time using the same colored box. In the other 3 demonstrations, it was the same individual dropping a ball 3 times to the other color box. Where the children and the chimps really got a ball later on, what they did is, of course, use the box that was used by many different individuals and not just the same individual over and over again. So it seems that we do pay attention not just to the raw frequency of something, but also to the number of sources that represent that. So if you go back to also the assumption that there really is that people who interact with fewer people then give more weight to each person, then that means that people with smaller social networks, should have more malleable representations. I now should say that if this is true, this is interesting not just for seeing how we learn something or update our representations, it might actually also have consequences for linguistic change. And I'll get back to it later. But first, let's start with seeing whether it is the case that people that have smaller social networks are really more influenced by each speaker they meet. So in order to test that, I basically modify the paradigm that was also already used by Yildirim and colleagues, and they basically show that people are able to learn and adapt to basically the lexical boundary between some and many when they're exposed to sentences such as some of the candies in the bowl are blue. So in my study, first of all, people needed to respond to the social network questionnaire, which I already used in quite a few other studies, and always people basically just need to list all the people they regularly interact with in a typical week. And then I just showed them these stars arrays that always had 25 purple and green stars, and they needed to say which of the two sentences, some of the stars are purple or many of the stars are purple, is more appropriate. Only this was in Dutch, so it was not some and many, but sommige en veel, but same idea. So they saw different arrays like that. And that way, I could tell what is their boundary between some and many. And according to that, I exposed them to a speaker whose boundary was precisely 2 steps away from their own. So if they started using many every time there were at least 11 stars, the exposure speaker started saying many when there were 13. If their boundary has been at 10, then the exposure speakers had been at 12, and so forth. And of course, the question is, would it be the case that people with smaller social networks would show greater influence of this exposure speaker? So I looked at that in 2 different tasks. First of all, I wanted to see how that exposure influences what they predict about new people. So I showed them new star arrays and asked them how a different speaker, and also showed them a different photo of a different Dutch woman, how they would describe these star arrays. And the idea was that if people with smaller social networks are more malleable, they should show greater influence from the baseline according to the exposure speaker. But of course, this is an individual different study. So if I get this effect, you might say, well, could it be that people with smaller social networks are just more motivated to do the task? Or maybe they're just better at learning the boundaries of speakers. So I also had another condition where I basically showed people, again, the same star arrays, but this time I asked them how the exposure speaker would answer them. And in this case, it doesn't really matter what your social network is. Everyone had the same exposure to the exposure speaker, so you should just use that knowledge. So I basically predicted that everyone, regardless of social network size, would be able to show learning of the specific speaker they were exposed to, but the smaller your network, the more you should generalize to a new speaker. But I looked not just at prediction. In addition to that, I also decided to look at production to see whether I actually changed the way they later on described new arrays. So I showed them new star arrays and looked at basically how much they deviated from their baseline in the direction of the exposure speaker. So if you look at the results, first of all, I'll start with a prediction task, and we see basically the interaction that I predicted between social network and speaker. And specifically, if you look at the new speaker condition, what we can see, so what I'm showing on the y-axis is the likelihood that they really shifted from their own baseline to basically what the exposure speaker said. So you can see that the smaller the social networks, the more they shifted, and I should say that it's not just the interaction that is significant, but also the slope. In contrast, if you look at the same speaker condition, we can see that everyone basically learned. So everything is much different from 0, so they're not sticking to the baseline, but they're moving to what the exposure speaker said. And there's no effect of social network size, and if anything, it looks as if it's going in the opposite direction. So people with larger social networks are quite able to learn the boundary of the speaker, but they don't generalize it to new speakers. If I look at production tasks, I basically see the same thing. I see that people that have smaller social networks are more likely to shift their boundary from from their baseline according to the exposure that they received. So together, what we see is that people that have smaller social networks are really more susceptible to the influence of new speakers. And the fact that the effect is really limited to the new speaker condition and doesn't happen in the same speaker condition shows that this is not just about differences in ability to do the task or in motivation to do the task. And I suggest that this is because the people that have smaller social networks basically give greater weight to each speaker that they encounter. Now, if we go back to the question that I said beforehand, can it have any implications also for linguistic change? When one of the puzzles of linguistic change is how do rare variants really get spread throughout the community? And what I'm wondering is whether people with smaller social networks, because they're more malleable, they'll be more likely, they'll be important for propagating, basically they'll change the behavior even if it's relatively rare because they're more malleable and therefore it will spread throughout the community. But one thing that you might wonder, well, people with smaller social networks, by definition, are connected to very few people. So can they really even have a lot of effect, even if they're malleable? So in order to answer this question, I tried to do a few simulations. So in all the simulations, I basically created a community of 1,000 people that just produced 2 vowels. And all these communities have free scale structure. So free scale, which is basically what people say is the structure of communities in the real world. And basically what free scale structure means is that, the number of people someone is connected to follows a power law. So that means there are very few people that are have very large social networks. But there are many, many more people that basically are connected to only very few people. And basically what I try to module in the simulation is basically the process of vowel merge. So I had 1% of the population really just produce the same format frequencies regardless of which vowel they were trying to produce. And importantly, I try to see what happens when they're connected to people with smaller social networks versus to people with larger social networks. So, for example, in one case, you see that this innovator is basically connected to only 2 people, but these 2 people have very, very large social networks. This innovator is also connected to two people, but these two people are not very well connected. And the question is, will we see greater vowel merge when the innovator is actually connected to people with smaller social networks, showing that having a smaller social networks really makes you important in propagating linguistic change? In general, I just had basically 50,000 rounds of interaction within the community, and every time two people interacted, basically they produced the vowels, and then the other person basically adjusted the representations according to what they received, and I assumed that there's an inverse relationship between how much you weigh each production and how many sources you have. And then I basically try to see what happens to the vowels, so the format frequencies across the population every 5,000 rounds of interaction. And basically what I found is that both a main effect of the size of the social networks of the neighbors and the innovators, and an interaction with time, which basically reflects the fact that when the innovators were connected to people with smaller social networks, I both saw in general greater merge in the community, and also this merge occurred faster, so the effect of time was larger all the time because the convergence was steeper. So, and I should say that actually plotted confidence intervals here, they're just so narrow that they're not quite perceptible. So, basically, what I'm hoping I convinced you is that I showed you that, first of all, people with smaller social networks are more influenced by basically different speakers. And with the simulations, I also showed you that this could lead them to play an important role in the propagation of linguistic changes. And I would like to thank you for your attention and to anyone who helped me in this study.
Okay, we've got a bit of time for questions.
I beat you to the microphone. Hi, Gail Monner from the University at Buffalo. So you haven't said anything about age here, but it seems like the people who have the smallest social networks are infants. Right? And so is there something to the fact that oftentimes they're the propagators of big changes in language? I mean, every generation we see changes in language. It's the next generation that's doing it. But when is that happening? Is it happening when their networks are really small, or is it when they're older?
Yeah, so there are different ideas about who are the propagators of linguistic changes. Are they children? Are they teenagers? There are different ideas. In general, I would agree that I should find even greater effects with infants, just because, yeah, their magnitude of the social networks might vary even more, and there are even smaller numbers, so every small difference might make even more of a difference. At the same time, I would say that I don't know if adults are as influenced by infants. So it could be that your 4-year-old is very much influenced, but would they influence back their parents? Or, so I'm not sure. I mean, so I would say, for example, in my questionnaires, when I ask people to report all the people they interact with, to avoid mothers putting all their children, I said to only include people above the age of 12, because I really assumed that below that it would not matter. So I'm not sure.
So somewhat related to this, when you mean smaller network, does that mean smaller network of people with whom you speak in the same language?
Yes. So in all my questionnaires, specifically asked them to only report about native speakers and not about interactions with non-native speakers.
But because that might bring up a population that could be really relevant for you, which is heritage speakers, who often in their heritage language, not all heritage speakers, but often they have a very, very small social network. Right? If the language is a minority language, like my children only speak Swiss German to me and my husband. So they should be super malleable. And one thing we know about heritage learners is that they display what has been called optionality on many grammatical phenomena. So maybe that is a result of them being just very adaptable, perhaps even in a test situation. So perhaps looking at heritage learners could help you out here.
Yes, I agree. But I think similarly, they would be influenced by native speakers of the language that are heritage speakers, or rather more than they by second language speakers.
There will be other factors, yeah, for sure. Thanks.
Thank you. That was really interesting. In the memory literature, item source bindings are a type of memory that's particularly susceptible to loss. So people forget where they learn sources from. And it leads to two interesting implications for what you're working on. One is that as you increase the number of potential sources that information came from, the baseline probability of making an error for where the information came from increases. And the other is the phenomenon in the memory literature, which is that if you hear a piece of information from multiple pieces of information, because those item source bindings are lost over time, people generate overconfidence for the truth of that information because they thought they heard it from, they lose whether they heard it multiple times from one source or from multiple different sources. And so I don't think your model included memory, but I'm wondering if you could sort of think about or say something about how the fragility of item source bindings might influence the way we think about this influence of social networks.
Yeah, so this is actually a really interesting point. I definitely agree we don't have great source memory, so it could be that sometimes it'll be a little harder to track. One thing that I do believe in is that we have some, in our representation, it's some hybrid model that has both exemplars and abstractions. And if you have exemplars, then at least, even if you don't remember specifically the source, you probably know something about the type of source. So I also think that, for example, you might be less influenced by most speakers that are, for example, I don't know, if it's something that depends on age or socioeconomic status or region, then more speakers of the same type will have less influence and more speakers from different ones because you'll differentiate your sources better. But I agree, right now I didn't include it at all, and I do think it's an important thing to think about.
Let's have one more question. Please state your name before the question.
Hi, I'm Dario. I'm from Potsdam, which is in Germany, not in the Netherlands. I think the model you showed at the end accounts for this, but not your experiment. So there's a new speaker coming in, and I adapt to this person's peculiar style of speaking. But when I go back to my small community, I again encounter people who talk like in the way I'm used to, and then my representation might actually change back because I'm more influenced by those people than a person with a larger social network. So in the end, that should all balance out, right?
Well, so two things. So first of all, I kept on using new speaker, but I don't think it's just about speakers, right? I use new speaker because it was easy to explain, and that's what I manipulated in my experiment. But I think the idea was that if I have a network that has 200 people and one of them says something, I'm much less likely to be influenced by that person than if I have a network of 4 people and one of them says it is. So it doesn't need to be a new person. It could be my regular network. In addition to that, I do agree with you. I mean, so I think it's the number of sources, but right now I did it a very reductionist way, as if we weigh all sources the same. It could be that like my regular network, I will weigh more highly than someone outside my network and other things, but so this might matter as well, but this is just the first step and it's very reductionist. Yes.
Okay, that's all the time we have. Let's thank our speaker. Okay, our next speaker is Russell Ritchie, and he'll be talking about conventionalization and reduction in an emerging communication system, an experimental and computational modeling investigation.
Okay. Is it okay if I just swap my computer in? Okay. All right, so thank you everybody for coming. So as they said, I'm going to be talking about conventionalization and reduction in the emerging communication system. I'm going to present an experiment and a computational model investigating this. So two processes tend to co-occur when new languages emerge and when established languages change. So first of all, languages are conventionalizing. That is, people come to agree on the word for a particular meaning. So English users conventionalized on frog, Spanish users conventionalized on rana. And at the same time, languages undergo reduction, meaning that linguistic expressions shorten over time. So in English, you don't have to say Elvis Presley anymore. You can just say Elvis. But this happens earlier in language emergence as well. So in the approximately, I think, 80 years old, Al-Said Bedouin Sign Language in Israel, the expression for dove was initially this compound of signs representing peck and some signs representing wings. And then later the expression was shortened to just wings. And famously, this also occurs in experimental settings like the Tangram studies, where people's ad hoc referring expressions for abstract little shapes undergo reduction as the expressions become common ground. So the question is, why do these two things co-occur? And while people have noticed the correlation between conventionalization and reduction, there really aren't many theories explaining why they are linked. One such theory comes from phonologist Joan Beide, who has said, quote, "I will argue that the reductive effect of frequency is related to the automation of production. This effect is related to the fact that language is conventionalized." So this theory might go something like conventionalization causes something to be a particular form or expression to be used over and over again. That way it becomes automated. Things that we automate can be done quicker. We can cut bits out of them. But that theory is not particularly explicit. It's not a particularly explicit or mechanistic theory. Certainly no computational models of it, for example. So in this work, we're attempting to develop a theory of conventionalization and reduction, which may be somewhat different, and then instantiate that theory in an agent-based model of communication. We'll show that such a model produces concurrent conventionalization and reduction. The theory and model have three key properties. First of all, agents have probabilistic lexical representation in production. There's a confidence threshold governing speakers' utterance length, and then listeners will adjust their lexicons towards their speaker's utterance. If the motivation for any aspects of this model seem a little odd right now, it should become clearer when I show the experimental data inspiring it, and then I'll walk through the implementational details of the model after describing the experiment. So in this experiment, we brought 8 groups of 4 hearing English-speaking undergrads into the lab. I'll refer to the groups as quads henceforth. Members of each quad repeatedly pair off and take turns describing and comprehending with gesture 25 objects. Essentially, they're playing charades, repeated games of charades with the same objects. On the right here is the basic setup. Two participants sit down across from each other with a visual barrier in between so they can't see each other's arrays. And then the describer looks at the booklet immediately in front of them to see the current target object. They get 3 images of an object so they don't focus on idiosyncratic details of a particular image. They then create a string of gestures for the target object, and then the comprehender attempts to pick the corresponding object from the array in front of them. Critically, no explicit, reliable corrective feedback is given. The describer and comprehender might try to decipher something about, the facial expressions on the other one, but that's about it. So then they switch roles back and forth until they have each described and comprehended all 25 objects. Then they switch partners and repeat the whole process. By the end of the experiment, every dyad has sat down together 4 times. That means that by the end of the experiment, 24 conversations or interactions have happened. Okay, so. So here I'm going to show the evolution of a single object, goat, in a single quad. I'm going to let you all watch this, and then I will talk about it. Okay, so this illustrates a few things. First, people tend to produce these sequences of iconic gestures, and it's fairly easy to identify what each gesture iconically represents if you, the coder or experimenter, know what the target object is. And then second, we do observe conventionalization. The different participants start out producing different gestures for goat, but by the end of the experiment, they've conventionalized on 2 gestures, one iconically representing horns, one representing beard. And then finally, we observe reductions. Their responses to go are initially about 3 gestures long. By the end, they're only 2. So as I said, most utterances are sequences of gestures like that. So we code each gesture for the aspect of the object that it iconically represents. And then we quantify conventionalization with the Jaccard index, which is a statistic for comparing the similarity and diversity of sets. It ranges between 0 and 1, 0 meaning total absence of conventionalization, 1 meaning perfect conventionalization. Sample computation will work like that. You have those 4 utterances from different people for goat. There's only 1 gesture in their intersection. There's 4 in their union. So the Jaccard is 1 over 4.25. And then reduction is just a decrease in the number of discrete gestures in an utterance. So going from something just like horns chewing to just chewing. And so here's the basic experimental findings. So on the x-axis is time, measured by the number of interactions or dyad pairings so far. In green is the Jaccard index, our measure of conventionalization. In blue is the number of discrete gestures in an utterance. And so while conventionalization as measured by the Jaccard index is increasing from close to floor to over 5.5, utterances are reduced from an average of 2.4 gestures long to about 1.8 gestures long. So again, why do these 2 processes co-occur? In the rest of the talk, I'll present a model that suggests one possible answer to that question. I already covered the basic principles of the model, so I'm just going to dive into an example interaction within the model. So as I said in the beginning, lexical entries are probability distributions over gestures. So our speaker might have a lexicon like that for, just with 2 objects, cow and goat, and then 3 gestures, horns, milking, and beard. So then when the agent wants to refer to cow, they would continue sampling that probability distribution until the summed probabilities for the gestures they've sampled exceed a preset confidence threshold. With a little bit of luck, the speaker will produce a string like that. If they don't, then communication will just fail, probably, and then no learning will occur, no harm is done, the agents just move on. They can try again on the next interaction. And then the listener simply picks the object with the distribution closest in Hellinger distance to that of the utterance. In this case, that luckily happens to be the target object, cow. And now the listener rewards and punishes their probability for cow in the direction of the utterance. They're just rewarding and punishing according to the linear reward penalty scheme. And so when you apply those update functions with some particular preset learning rate, you get the values in the column cow prime in the middle there. And then finally, we renormalize the updated probabilities, and this interaction is now done. So returning to our phenomena of interest, updating lexicons in the direction of a speaker's utterance accomplishes conventionalization, and reduction occurs because probability over time becomes more concentrated on a smaller set of gestures for a particular object. That then means that the next time the agent speaks, they clear the confidence threshold by sampling fewer gestures. And here I'm plotting simulation results showing that this is indeed the case. As with the experimental plot, the x-axis is just time as measured by the number of interactions. Blue curve is utterance length. The green curve is conventionalization measured by the Jaccard index. This is 16 simulations with 4 agents each, talking about 4 objects with 3 different gestures. I can go over the full array of parameters in these simulations at the end if people are interested. So to wrap up, consistent with previous empirical work, our experiment and model show concurrent conventionalization reduction. However, our model is the first, to my knowledge, to model these 2 phenomena simultaneously by a combination of 1, probabilistic lexical representation and production, 2, a confidence threshold governing utterance length, and 3, listeners updating the lexicons in the direction of their speaker. This theory strikes one as different in some ways from the automation-driven theory of Joan Beide and perhaps others. So what we're doing right now is we're further exploring the parameter space in this model and also assessing other potential theories of the link between conventionalization reduction, theories that have kind of a listener-oriented or a speaker-oriented flavor to them in both our experiment and in our model. And with that, thank you.
Okay, we have some time for questions.
Thank you.
Please state your name.
Oh, do you want to?
Sorry, I had a little bit of trouble getting over here. Is this on? There we go. Yeah, I wanted to ask this very interesting work. I do work on gesture, co-speech gesture. So I was wondering, oh, sorry, my name is Laura Moret, and I'm from Yale and University of Alabama. So as I was saying, I do work on co-speech gesture. I mean, this is obviously, you're looking at this in terms of sign language, and then it's applications to spoken language as well. But what I wanted to ask is, do you think this theory that you have, or these results, do you think they generalize to paralinguistic signals, so things like co-speech gestures or other affective cues, possibly?
I haven't thought about that so much. Now, perhaps, I mean, I guess we do conventionalize certain kinds of co-speech gestures, like, you know, that and...
Yeah, especially iconic gestures.
Yeah, yeah. And I would imagine that we probably... I don't know this for a fact, but it seems very reasonable that we would reduce those as well in certain respects. So that seems plausible to me. I'd have to think about it more, though.
Yeah, sure. Thank you very much.
Yeah, thank you for the question.
My name is Sarah Brown-Schmidt. I'm at Vanderbilt University, and I'm going to answer your question. So, and I didn't know you were going to ask that. So, and I was going to tell you, so Katie Hilverman and Susan Wagner-Cook have a series of really interesting findings with co-speech gestures in the Tangram task, where they find that co-speech gestures reduce over time, and they also are sensitive to the status of common ground. So in the same way you see recovery of long NPs in spoken versions of the Tangram test when you speak to a new partner. You see the same thing with co-speech gestures. And so the way you were talking about the reduction in the iconic gestures was predicated on the fact that it's like information that they're communicating. But in the co-speech gestures in the Tangram task, most of the information, I think, is being communicated in the words. So I'm wondering if you can say more about why you might get this effect with co-speech gestures, and if maybe you're
Well,
tells you something about your own
I would
data.
want to look more at that study. I'm curious, you know, I don't know if you can answer this question or if I should just go read the paper myself. But how do we know that the co-speech gestures aren't conveying information that the comprehender is picking up?
They're not looking.
They're not looking. Okay, well, that's pretty good reason. Yeah. I would have to look more at that paper and think more about this. Yeah.
My name is Sabi. I'm at UC San Diego, and I have yet another example of reduction.
Hi. Nice to meet you.
Nice to meet you. Well, so another reason that we might think reduction is happening in a non-meaningful way is you find like physical reductions. This is something that we've measured, but obviously like it's difficult to measure that for reasons that you know about.
Yep.
But I have a different question actually, which is about how do you get, so you start with like horn or like beard horn, like, so what do you think about that distribution? Like how do people, what types of features do people focus on in their like round one?
Yeah,
And is that
right.
part of your model or something you're interested in?
Right, so the model right now does not incorporate anything about sort of what people find most natural to select from objects, kind of the most iconically salient features perhaps. There's nothing in there, but that's a very good thing to select. As far as what what people are doing, I'm not sure. I think people have sort of non-linguistic, possibly, representations of these objects. Certain features feel to them more central to the quality of that object, and so they decide to iconically represent that. For the time being, I don't know if I can get any more specific than that, but it's definitely an important question to think about. Yeah.
Hi.
Hi, Gerardo Ortega from Max Planck Institute. I really like this study. Thank you very much for this presentation. I have some questions kind of related to that. My question is, like, did you find that from the very beginning, at the onset of the task, did your participants were already quite systematic from the very beginning, or did you find... the reason I'm asking is because we've also found in pantomime, in one single round, and also with in the Netherlands and in Mexicans, that they're very systematic from the very beginning.
Yes.
In the representation of objects, actions, and non-manipulable objects. So I'm asking this, like, in this domain in animate entities.
Yeah, so you mean systematic in the kinds of semantic features they like to represent?
Yeah, like how many participants selected the horns and the beard and, you know.
Yeah,
like
so I don't think with this data set I've done a particularly systematic sort of categorization of the different kinds of gestures people, but I can tell you kind of impressionistically is that people do everything for, you know, ranging from the typical actions that objects afford to, you know, in the ways you handle them, to representing the shape of the objects. Probably very similar sorts of things that, you know, you're used to seeing.
Okay, yeah, it would be really interesting to see whether you find any pattern, because my prediction is that they would always, well, they, at least for many items, they would converge in the features that they pick.
Say that again, sorry.
So I would imagine that many participants would converge in the items or the semantic features that they pick from the different animals that they had to represent.
Yes, participants do that. Now, one thing I didn't mention here is that you might think that because this task is so highly iconic that the different groups would end up doing the same things. They don't. Different groups do conventionalize different systems. I have a plot showing that, but maybe we don't have time to go through that.
Okay, thanks.
Yep.
Can I make one quick suggestion?
Sure.
Really quick. Okay. I just have a quick suggestion about where you might want to look for conventionalization in co-speech gesture. Look at scientists. Look at maybe linguists too. When they talk, they come up with, like, if you've looked at David McNeil's mathematicians talk together, they have a particular gesture that they use for inverse something or other.
Knowledge of syntactic universal guides, knowledge of a syntactic universal guides generalization to new structures.
Thank you. So it's probably not by accident that the world's languages look the way they do. So for instance, in English, I might describe this picture with a subject-verb-object word order, something like the girl hugged the bear. And if word orders arose by chance among the world's languages, then we'd expect an even distribution relatively. So a sixth of all languages should have a subject-verb-object word order like English, and a sixth should have SOV, et cetera. But we know this isn't the case. So in reality, almost 90% of the world's 6,000 languages are probably somewhere in these first two categories, and then the rest are sort of distributed throughout the rest. And this suggests that there are pressures that diachronically lead to the distributions that we see, these sort of skewed distributions. And so Vic and I in this project are asking if we can recapitulate the pressures that lead to these distributions in the lab, in the learning of individual subjects. So to do this, I'm going to move to the domain of relative clauses. And just a brief refresher, relative clauses are clauses or sentences that modify nouns. And so in this first example, we have a subject relative clause describing the girl in this image. So we'd say the girl that hugged the bear. And within the relative clause, we don't repeat the noun that's being modified, and we call that position a gap position. So this relative clause has a subject gap. We can also put a gap in object position, so we can describe the bear by saying this is the bear that the girl hugged. And so on. So gaps can go in a number of positions throughout, or in a number of positions where arguments go. And this pattern was characterized by, So not all languages can put gaps in all positions. It turns out that there's actually a pattern to it, and the pattern was characterized by Keenan and Comrie in the 70s. It's the noun phrase accessibility hierarchy. And it goes like this. So if your language allows gaps in a given position on the hierarchy, so for instance, direct object position, then it also necessarily allows gaps in positions above that on the hierarchy, so subject position, but not necessarily in positions below that, for instance, direct or indirect object or oblique positions. So it's hard to find a case where this looks like it's relevant for English, but maybe you're finding these sorts of constraints cropping up in genitive positions. Like in English, you can't say the man that I walked's dog or the man whose I walked dog. So there's one other dimension of variation in relative clauses that's relevant here, and this is the position of the relative clause. So in English, we put relative clauses after the nouns they modify, and therefore we call them post-nominal. But in a number of languages, like Chinese, the relative clause comes before the noun that it modifies. So a subject relative clause in Chinese might sound more like that hugs the bear girl. And similarly for object relative clauses, that the girl hugs bear. So we taught participants to produce prenominal relative clauses in the lab. And the way this went, there were two training phases. So in the first training phase, participants got 36 images, and an experiment was to describe each one with a prenominal relative clause. So I don't know how well you can see these pictures, but the first picture is of a man throwing a frisbee. And so this would show up on the screen. There's an arrow pointing to the man, and the participant or the experimenter would say, "That's that threw a frisbee man." And then they would see the next image, and the experimenter would say, "That's that discovered a fossil archaeologist." And then those same two pictures would come up again in random order, and the participant would have to try and recall it the way the experimenter had said the sentence originally. So you'll notice that these are subject relatives that I just gave you. There were 3 training groups. So we gave one group exposure to 36 subject relative clauses prenominally. Another group, 36 prenominal object relative clauses. So for the first picture, that would be that the man threw frisbee, or the second image would be that the archaeologist discovered fossil. And then a third group got half of each, so 18 prenominal subject relatives and 18 prenominal object relatives. In a second training phase, because this was difficult, participants saw the same 36 images again, and they had to recall the sentence, they had to try to recall the sentence the way the experimenter had described, and they were told that they wouldn't get help unless they had tried something. So they had to produce something, and then the experimenter would correct them, and they would go on to the next trial once they said something that fit our grammar. And then in the test phase, they got 36 brand new images that they had to describe, but we did something sort of tricky. So we gave them the verb. So in this first image, we gave them is poking, and we pointed to the demon here. So they would have to say a subject relative, something like that is poking the angel demon. And in the second image, we give them the verb sprayed, but this time we point to the object of the verb sprayed. So they would have to say something like that the elephant sprayed clown. These get remarkably easy and start sounding normal after a while. It takes a while, but. So in this way, we were able to manipulate whether or not we were eliciting a subject relative or an object relative. And for all 3 groups, we elicited 18 of each. We included a 4th group, which we called an explicit group, where we gave people explicit instruction about what a prenominal relative clause looks like. So we showed them a post-nominal, a standard English relative clause describing this image. That's the teddy bear that the girl is hugging. And then we explained that relative clauses are sentences that modify nouns, and they can come before or after, and in English they just happen to come after the noun they modify. And that in Chinese, for instance, they come before the noun they modify. This group skipped the exposure phase altogether and went straight to the same test phase that everyone else had. Okay, so predictions. As for learning, we might predict that object relative clauses will be learned less well than subject relative clauses based on this long literature showing that object relative clauses are harder to process than subject relative clauses. And so this is depicted in this graph by the shorter blue bar. So what I'm plotting here are congruent responses. So the subject relative clause exposed group is on the bottom left, and subject relative eliciting trials are in red. So congruent responses would be red here, and they are plotted as doing better at producing subject relatives than object relative exposed people were at producing object relatives here. And so the question we have now is about generalization. So what's going to happen? Well, what might happen depends on what you think, what kind of knowledge you think participants are using to make generalizations, if they generalize at all. So on one possibility, they're using their knowledge of English. All of our participants were native monolingual English speakers. And so English has both subject and object relatives, and maybe there's some sort of implicit reasoning going on, something along the lines of, well, if you're in the object relative case, I've learned all these prenominal object relative clauses. These look a lot like this object relative clauses I have in English, just they come before the noun. So now that I'm being asked for a subject relative clause, I can just take this subject relative clause from English and stick it in the same place they've been putting object relative clauses, something like that. If that kind of thing is going on, if people are using their knowledge of English to make generalizations, we might expect symmetrical generalization. So that subject relative exposed people will produce as many object relatives as subject relatives, and the same for object relative people. On the other hand, people might be using more general knowledge of language to make inferences. And if that were the case, then we might expect that the same sorts of asymmetries that crop up in the world's languages should show up in their generalizations. So maybe if people are, so for instance, an object relative exposed person, they are able to make the inference that because this grammar has object relatives in accordance with the accessibility hierarchy, it should also have subject relatives. But the same shouldn't be true for the subject relative exposed people, because not all languages with subject relative clauses have object relative clauses. And if that kind of reasoning is at play here, then we should expect to see an asymmetry like this one. So I'll go ahead and skip to the data. So the explicit group, remember this is the group that we gave an explicit grammar lesson to. They didn't do very well. They got about 7% right, shocking. Especially compared to the group that received training on 18 of subject relatives and 18 object relatives. And so these people did pretty well. They were about 50%. They did slightly less well on the object relative clauses, which it doesn't look like a big effect, but it might be due to something about differential processing difficulty. The people who only received object relative clauses were somewhere in the middle in producing object relatives, and the people who were exposed to a bunch of subject relative clauses did the best overall in producing congruent responses, so subject relative clauses. And so as for generalization, we find this sort of asymmetrical pattern where the people who were exposed to subject relatives did not generalize as much as the people who were exposed to object relatives, both in number and in proportion. And this comes out as statistically significant. So this is inconsistent with English, and I'm claiming that it's consistent with the accessibility hierarchy. There's one caveat here, though. So if I'm eliciting a subject relative, there's really only one thing a participant can give me, a subject relative. So just standard English relative clauses, you could describe this top picture as the girl that hugged the bear. But when I elicit object relatives, there's actually two things people can do. They can give me an object relative, like that's the bear that the girl hugged, but they can also passivize the relative clause verb and turn it into a subject relative that means the same thing. So that's that standard English. That's the bear that was hugged by the girl. And there's no parallel transformation that can take a subject relative and turn it into an object relative. So this might have given the subject exposed people sort of an unfair advantage. Maybe advantage is the wrong way of talking about it, but it could be that they didn't do the same amount of generalization that the object relative exposed people did, not because they weren't able to, but because there was a way of producing a sentence that meant what they needed it to mean, but that was congruent with their exposure. And so if we look at the number of passives produced here, you actually see that that for the subject relative group on the left, they actually did produce a number of passives. These are the green bars. And there's still an asymmetry. It still comes out in the statistics, but we wanted to rerun it and see if we could block passives altogether to see if this would hold up. So in a new training group, we changed the verbs. So part of the problem was that the verbs we had given people were sometimes ambiguous between past tense and participle forms, and participle forms can be in the passive construction. So we changed all the verbs to be clearly finite and not participle forms. Although it's interesting because apparently some English speakers anyway, younger generation, use past tense forms as participle forms. So we still get a few passives, but and we enforced that people use the verbs as they were written. And so the new data are here on the left. This is the first 16 people. We've run 24. I haven't coded them all yet. And the asymmetry is still there. I haven't done statistics on it. It's a little bit less strong, so we'll see what happens with that. So to recap, object relative clauses were harder to learn than subject relative clauses. The object relative clause only group generalized more to subject relative clauses than the subject relative clause exposed group generalized to object relative clauses. which I'm claiming is inconsistent with English and consistent with the accessibility hierarchy, and suggests that speakers were drawing on some general knowledge of language as opposed to language-specific knowledge to make these generalizations. I've been focusing a lot on that point. There's a more basic point that I think is pretty cool here that I haven't really focused on at all, which is that participants were actually producing structures they had never been exposed to. So somehow they had generated this representation or something along those lines that they had never seen. So I think that's pretty cool. In conclusion, synchronic language learning is recapitulating here diachronic language evolution. And our next step is going to be to try to identify the pressures that are leading to this asymmetric generalization we're seeing. Thank you.
Okay, we've got a little bit of time for questions.
Thank you. I'm Emily Morgan from Tufts University. I want to ask about really what you've, I think, listed as your next steps, so about these pressures that could be leading to the asymmetrical generalization, because you've talked about people drawing upon some general knowledge of language, but I find it a tough sell to believe that somebody who has only grown up ever speaking English has some implicit generalization about what all languages possible would do and is drawing upon knowledge in that sort of explicit form about what possible languages are when they're doing this task. So I'm assuming from the way you sort of phrased that last point that you're thinking in terms of other maybe processing pressures or representational pressures or something like that that could sort of lead this asymmetry to emerge. So I'm curious kind of what directions you're thinking in there.
Yeah, I'm being maybe a little too flashy with the way I talk about this. I mean, it's hard to say. Ultimately, the question here is what pressures are leading to the distribution, right? So what's leading to the accessibility hierarchy? And this could just be something about the differential processing difficulty that we see in between subject and object relative clauses, and presumably all the way down the hierarchy. I don't know. It's what we want to target next. It's a really interesting question, I think. Thanks.
Thank you.
Is this on?
No.
Al Kim, University of Colorado. Isn't there a simpler explanation that doesn't require saying your generalization pattern is not consistent with English, that the ORC structure is harder than the SRC structure, and so it's harder to learn to use the ORC in a new situation than to use the SRC in a new situation?
Yeah, that's possible. So the analogy that my advisor Vic has used for this is in board games. So if you teach someone chess, it's going to be easier for them to learn checkers than vice versa. Yeah, I think that's reasonable. It's totally possible that that's what's going on here. It's also possible that that's what leads to the distribution of relative clauses we see across languages. So I think that it's an interesting question either way. One way we were trying to get at that now is by using verb final relative clauses. So just sort of taking away any possibility that people are relying on knowledge of English to get to generalize to new forms of relative clauses. So we'll see what happens there. Thanks.
So, Mary Ellen McDonald, in addition to Al's, I think, very good point, I wanted to ask or point out a little bit about the use of passives, because use of passives is not equal for every kind of event. Mm-hmm. And in English, animate patients are going to get passivized much more often. So to the extent that you see that in your data, you have evidence of people using their knowledge of English in what they're doing. So it's another point about, it's a little implausible that people are not extending their knowledge of English in this case.
Yeah, and actually if you look at the items where passivization is most common, it's the ones with asymmetry and inanimacy between the arguments.
One more question.
I'm Sharon from the University of Rochester. I know that Chinese is just a metaphor in your case, but in Chinese the relative clause is left branching, and also the relativizer is actually at the end of the relative clause. So rather than that is hugging the bear, the girl, it's more like it's hugging the bear, that the girl. Do you think they will cause some difference to the learnability of different structures?
What was that last line?
If you move the relativizer to the end of the relative clause, will it cause
There were a bunch of sort of not optimal choices we had to make when we were designing the grammar here. I don't think as far as I know, there are no languages with something like a complementizer at the beginning of a pre-nominal relative clause. I think they're all adpositions at the end of relative clauses. And one of the problems you ran into when we tried that version of the grammar is that you get two determiners in a row. So it would be something like that's a boy was throwing balls. There's no optimal solution to the problem. So maybe a nice follow-up to do.
Thank you. Okay, let's thank our speaker. And that concludes our session.
Hi, I got 3 announcements. First, I neglected to mention this morning that Bill Badaker from the program in linguistics at National Science Foundation is here. Bill, can you wave or stand up or something? And if you would like to talk to him about trying to get funding for your project, he is available. He asked me to tell you that he wants to meet with you if you want to do that. I am not just sending him askew. Okay, second, these next 2 are not so important, but there's a webcam which is filming everything, which is over here, and it's filming everything now and also in the breaks. And so if you're going to stand here and talk, you are being streamed live. It's not going to be captioned, but that material will be there. So I look where the thing is filming and maybe don't stand there or don't talk too loudly around there. And then third,